Okay. Something is happening. Did it work? I guess so.
Yes, of course.
Okay, thanks. Everybody can hear me, right? On Zoom. Whenever you were here, of course. There's an echo.
Onur.
Okay, thanks.
Yeah. Some of these are.
Okay. Yeah, I think we can get started. Okay, great. So today we're going to wrap up prefetching, which we have almost finished, but I want to wrap it up a little bit more. And then we're going to talk about multiprocessors and memory ordering. Now we've come to the part of the course where we will talk a little bit more about computation. But you will see that even this part of the course is dominated by memory. I mean, such a fundamental topic like multiprocessors. We'll talk about memory issues, essentially, like memory ordering, cache coherence. All of the interesting things are really related to memory. If you haven't gotten that feeling yet, you will see that even more over here. And also interconnects. So we will build up to interconnects. We could have covered interconnects earlier, but I like pushing it a bit later so that you understand the context of why they're so important going into the future. Because they are going to be extremely important also. When we talk about interconnects, hopefully you will see that. Okay, so let's get started. But before, as I said, we'd like to wrap up prefetching. We were talking about run-ahead execution. I'm not going to cover that again. I'm going to tell you the story of it a little bit, but not cover it much. So essentially, if you remember, run-ahead execution was an execution-based prefetcher, which used otherwise idle cycles where the processor would be stalled for prefetching purposes. And it's a purely speculative execution mode. And the idea of an execution-based prefetcher was very similar. Pre-execute a piece of the program solely for prefetching data. It could be a prune piece of the program. And run-ahead execution in its original form did not prune the piece of the program, basically. It just executed the piece and dropped the instructions that it couldn't execute because if their data was unavailable. So run-ahead execution is really an execution-based prefetcher. I've already said this. There are advantages and disadvantages of it compared to other execution-based prefetchers. We will discuss that a little bit in the next slides, I think. But clearly, run-ahead doesn't use any context, doesn't require any other context. What happened here? There's some connectivity problem. Okay, let's hope that it doesn't happen again. Some bit flip maybe somewhere. Yeah, but basically, run-ahead doesn't use any other context. It's just the main program is already running. You just switch to the speculative execution mode by checkpointing the architectural state and restoring the architectural state to switch back. So it's actually very frugal in terms of the hardware it demands. Compared to other prefetchers, other execution-based prefetchers, usually they require some other hardware context to spawn a thread to do prefetching or branch prediction, as we have discussed, or some other core to do it. There are proposals that actually build on run-ahead that say, okay, instead of stalling, let's switch in some other thread to do prefetching for the main program, kind of like run-ahead does, but run-ahead does it very automatically, right? You don't need to create a separate thread in run-ahead. So in that sense, it's very frugal. It's very low cost to enable that thread. And then we asked the question, can you make run-ahead even better by pruning the program portion executed in run-ahead mode? And we have actually seen that. Continuous run-ahead is an example of this. As I said last time, this is a major improvement over run-ahead more than 10 years later after run-ahead was discussed. So basically what we're doing with the run-ahead is, and also in speculative threading, per-execution-based prefetching, is we're taking advantage of pure speculation. And this is actually very nice, I think. You're purely speculative. The goal is to find and generate cache misses that would lead to execution stalls, because they would actually have long latencies to service from memory. And then the question, of course, if you really want to make it even more efficient, this is a good question to ask. How do you achieve this goal most efficiently and with the highest benefits? And the idea is to find and execute only those instructions that will lead to cache misses that cannot already be captured by the instruction window, because you have some out-of-order execution window. And within that window, you generate some of those cache misses automatically anyway, right, in the processor. If you already capture the cache misses, that's great. You've already parallelized them. But there are some cache misses that are far away that this out-of-order execution window cannot capture, and those are the ones that you really want to target. Right? And this idea has been powerful. People have been looking at this idea, and I think continuous run ahead actually. How do you do that? Continuous run ahead is an example of this, but I don't think this idea is done yet. There's more to do in this area, frankly. So if you're actually interested in doing research in this area, there's more for sure. So as you can see, continuous run ahead happened 13 years after our original run ahead paper. I've also mentioned some of the other run ahead papers very briefly, but you can also do the readings. But I believe it's actually a nice approach. The idea here, if you remember, was to have a specialized engine in the memory controller that gets dependence, like a dependence chain, and it keeps repeatedly executing that dependence chain so that it can generate cache misses. And as we have discussed, you would actually go execute 100,000 instructions or so. So you would actually run ahead really far away, as opposed to being limited by the amount of time you stall otherwise, right? Which is really the memory latency, but not necessarily the memory latency, because some of that memory latency may have already been covered because of prefetching, etc. So I believe that this is actually a much nicer approach going into the future. It's more costly, of course. It's less frugal than run ahead execution. But now you can think of the program as being parallelized. You have a main program running, and you have a speculative engine that keeps prefetching for the main program. And that way, main program hopefully will never stall. If you actually build this nicely, that speculative engine never ensures that the main program doesn't stall for long latency cache misses. As I said, this is not done completely, and there's complexity issues, but I think there's a lot more research to be done in this area. Okay, so let's talk about execution-based prefetchers, pros and cons. The beauty of these prefetchers is they can pretty much prefetch for any access pattern, right? They have difficulties prefetching for dependent cache misses. Actually, if I go back, continuous run ahead doesn't do that, but there is a work that Milad did. Well, how does this work? Okay, this is very small. Milad, in his dissertation, this was one of his contributions. The other contribution was to have a memory controller that actually does fast linked data structure accesses so that dependent cache misses are uncovered quickly. So if you combine continuous run ahead with an engine like that, we call this an enhanced memory controller. And basically you can cover both dependent and independent cache misses. So that's another speculative prefetching engine, basically. Okay, can be very low cost. For example, run ahead execution is very low cost, especially if the thread uses the same hardware context, because the processor is already equipped to execute the program anyway, right? The processor is already doing a lot of stuff. You're just using the existing context to execute the program. Can be bandwidth efficient. Run ahead execution is actually very, very bandwidth efficient. Many works have shown that. Your accuracy is very high, and you're not really increasing the cache misses that much. You're not basically prefetching something useless in general. But in general, the execution-based prefetchers, of which run ahead is an example, they depend on branch prediction and possibly value prediction accuracy. And as we discussed, mispredicted branches depend on missing data, throw the thread off the correct execution path. So you go onto the wrong path and execute in the weeds without knowing that you're on the wrong path, right? And that is not necessarily good, but that's not necessarily terrible also, especially if you're going to go to that path at some point anyway. And if your data values are somewhat okay, so that you can prefetch data on the wrong path, that will be useful for the correct path later on. So certainly there could be benefit on the wrong path. And we've analyzed this a lot actually in our works. And we've shown that if you have the option of not going on the wrong path, don't take it. Meaning on average, go on the wrong path during run ahead mode. That actually brings you prefetching benefits. But of course, if you have the option of correcting that branch and being on the correct path, that's better on average. So wrong path is beneficial compared to not going on the wrong path, but being on the correct path is better than being on the wrong path. So that's the takeaway, basically, which is interesting, actually. There's a lot of interesting analysis of it. And then these prefetchers can be quite wasteful because you normally speculatively execute many instructions. And we've seen that in run ahead, and we've tried to solve that problem. Continuous run ahead actually solves that nicely, I would say. Because main run ahead just executes the entire program. It doesn't really think which instruction will lead to cache misses, which instruction will not lead to cache misses. So in fact, that's quite wasteful. Okay. And then it can potentially occupy a thread context. That's another example of waste. Right? And then there's complexity clearly in these prefetchers in deciding when and what to pre-execute. Runhead eliminates a lot of that complexity because it basically executes the main program. But if you really want to optimize things further, like continuous Runhead does, you need to really figure out what to execute and when to pre-execute. And these are decisions that you need to make in any kind of execution-based prefetcher. Any questions or thoughts? Yeah. Maybe you can press the button. So we should really exercise that. Yeah.
Yeah. So the question will be like, in some cases, when you are actually pre-executing some instructions and you are going much faster than the current program, for example, you can fill the caches in a way that actually the data that you're putting there, if your cache is too small, then the real program that the processor is executing then doesn't really get this data.
Exactly. So it gets evicted before the main program gets to it, right? Yeah, that could happen if you're executing very, very far ahead, certainly. And we don't see it as much in Runhead, for example, because it's not executing too far ahead. But with continuous Runhead, it could actually happen. Yes. So you need to be a bit careful. Yes, you had a question also? Is it the same question or?
No. Okay. How do you know that the topics you research, or do you know if the topics you research have been implemented like in a hidden in a commercial design already?
Yeah. For this one, I'm going to tell you the story. It's implemented, Runhead, because people actually wrote papers about it, major companies. But again, you don't completely know, right? Someone can implement your idea and never tell anyone about it. It could be in a processor, because this is how it works. It's open research. It's not even patented. We don't patent our research. Yeah, even if it's patented, someone can still implement it and not tell anyone about it, right? So basically, the best answer is the best way to know it. Of course, hopefully, some company who implements it writes a paper about it, right? Or actually publish patents about it, referencing your work. That happened in case of Runhead a lot, for example. But there are other ideas where people implement and they actually maybe sometimes tell you. That's another way of knowing. That's not the best way of knowing, clearly, right? If company goes public about it, that's much better. And sometimes they don't even tell you. And I've seen all of those cases, basically, in my research, particularly. Does that make sense? Yeah. Yeah, I mean, I guess that's the beauty of doing research, right? You can have impact without knowing that you've had impact. Yeah. Okay, so basically this is a paper. I think you will read it at some point. But efficient Runhead is actually important also. These are all part of my PhD thesis. And then we also tackled, as I mentioned last time, how to predict the data values of loads that will lead to other cache misses, basically dependent loads. And we have a mechanism that actually does that nicely for a limited set of loads if your memory allocation patterns are nice. It's limited, but I think it's a simple, easy idea. You can take a look at that also. And then you can find my dissertation and other lectures that go more into detail in Runhead in the past, but I will not talk about them. As I mentioned, I think there have been improvements on Runhead more recently also that I don't include over here. Maybe in a future version of the lecture, we can include them, but I think continuous Runhead is a major improvement. So basically, this is an answer to your question. This is a presentation from Sun at the time, where basically they describe one Scout and they basically say it's Runhead. And then they basically show the benefits that they get. We've discussed this last time, right? So presentations could be another way of seeing it. But they've also written papers about it saying this is a version of Runhead. You can read that. And they've actually enhanced it in different ways, which made it a lot more complicated if you actually look at it. But you can look at it. There are interesting ideas here, but that makes the processor quite complicated because their goal was, in this work, their goal was to go Runhead so that they can capture the cache misses, prefetch the cache misses, but also while they're executing the instructions, okay, these instructions generated results, let's reuse them as well. In our early work, we argued that this is not a good idea because it adds a lot of complexity and also not a lot of benefit. In their work, they add a lot of complexity and argue that there's benefits. So the jury is still out. But the difference, I think, is they had a much more in-order processor. We were looking at a much more, let's say, state-of-the-art out-of-order processor, where reusing some of those instructions really doesn't help you because they're not on the critical path of execution in the end. Okay, but it's another example where IBM actually wrote a paper about it. You can see that they actually have it in the title, and they analyze it. And actually, this is I like this one a lot because this is I mean, I like all of these. Clearly, they're taking the idea and they're implementing a variant of it in real life, and then they're describing basically their experience, which is good, I think. In fact, if I go back over here, the results that Sun has are very similar to the results that we had reported for in-order processors. So we basically showed, in a similar configuration, we basically showed about 40% performance improvement. They also show about 40% performance improvement. So it's good that your results are validated by people who actually design processors, right? This NVIDIA, this was their, in their SoC, system on a chip, they had a CPU also in addition to a GPU. And they decided that CPU has run-ahead execution. There are a lot of ideas. There are a lot of good ideas in NVIDIA Denver, actually, dynamic compilation being one of them. But they basically also give results, as you can see over here. But I'm not going to read it, but you can see that there's significant performance benefit over a baseline that has a nice hardware prefetcher. And these they actually report the benefits compared to the hardware prefetcher, and they see significant improvements. These are also very similar to what we report, by the way. Anyway, you can read more if you're interested. So I think this answers your question, hopefully. But this doesn't always happen, right? Now, let me give you some perspective of I clearly was very invested in the research, right? This was my doctoral dissertation. And the way we were thinking at the time was interesting. This was early 2000s. And there was a huge focus in research on increasing the size of the instruction window, which is, you have an out-of-order instruction window. At the time, it was 128 or so, and people were trying to get to 512, and they were designing a lot of complex mechanisms. We were thinking a bit differently. We wanted to basically not design bigger, more complicated machines. We wanted to be more efficient, let's say. And I think that's where run-ahead made a big impact. We wanted to keep the out-of-order core simple and small, and at the expense of some of the benefits of out-of-order execution, like non-memory related. Okay, some instructions take 5 cycles, 10 cycles, 15 cycles here and there. They're not important. That's the mindset, right? They're not that important. Let's make big things. Let's reduce the latency of big things quickly. And maybe we can handle those other things in some other way. And that was the insight with run-ahead, I would say. And the goal was to really aggressively use automatic speculative execution solely for prefetching. And you can see that. And the beauty of this is it's synergistic with other prefetching and branch prediction methods. So it doesn't really go against any of them. It can be combined with many other prefetchers. And after that, a lot of interesting and innovative ideas ensued. But I should also say that this is not the first work in run-ahead. Actually, this is one of the first works in run-ahead that I could find. It basically has a very similar idea, but it was not really interesting in general. It didn't have a whole lot of impact because it was looking at a very simple processor. So this is 1997. This was looking at a 4-stage pipelined MIPS type of processor, in-order processor. And it was trying to tolerate L1 cache misses. So people, maybe unfortunately, maybe unfairly, didn't believe that this would have impact in a very complicated, sophisticated processor that already had an out-of-order execution window that implemented out-of-order execution. So I think these folks actually deserve a lot of credit for really, I would say, inventing run-ahead. And when we actually first looking at the idea, we didn't know about this paper, interestingly. We called run-ahead scratch mode execution. So scratch mode execution meaning you do some prefetching, and after you're executing, you scratch everything else, right? That's another idea. Right? But then we discovered this paper before writing our paper, and it said run-ahead, and we basically used their terminology. I think that's very, I believe what we have done is right. We could have, let's say, cluttered the literature by calling run-ahead scratch mode execution. Instead, we basically use these guys' terminology, which I believe is the right thing to do. Because their terminology, there's no problem with their terminology, right? Yeah, I think coming up with new terminology is not that great, and people like doing that so that they can distinguish themselves from past work, but that's not a good idea in general, I would say. Does that make sense? Yeah. Say it again. I don't know. You have a question? Okay, yeah. Yeah. Okay, any questions? I would also mention that you guys should read papers like this. Is a single page paper. This is the entire paper. It's more of a let's say manifesto statement, and this was an inspiration for me when I was doing my PhD. This is Andy Glue. He's actually a computer architect that I worked with in the past also. But basically, I cannot read this over here. I used to be able to read it somewhere, maybe when I was younger. But basically, he argues in this paper that imagine that a cache miss takes 10,000 cycles to execute. For such a processor, instruction level parallelism is useless because most of the time is spent waiting for memory. Branch prediction is also less effective since most branches can be determined with data already in registers or in the cache. Branch prediction only helps blah, blah. It only helps for branches which depend on outstanding cache misses. At the same time, pressures for reduced power consumption mount. Given such trends, blah, 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 I propose something different. Build narrow, fast machines, but use intelligent logic inside the CPU to increase the number of outstanding cache misses that can be generated from a single program. So this is kind of the run-ahead mindset also. Basically, the solution, first change the mindset. MLP, memory level parallelism, is what matters, not ILP, instruction level parallelism. Of course, it's an extreme thing, right? Anyway, I'm not going to read all of this. I would suggest you take a look at it, but there are a lot of ideas in this paper. Clearly very high level ideas, but this is everything. This is how everything starts, basically. You have to basically understand what the real problem is, which this person is trying to do, and basically argue that maybe this is the solution direction, and then hear a bunch of ideas to really solve the problem with that different mindset, right? For example, let's pick one example over here. Build one wide processors that are as fast as possible. Use circuit tricks as well as logic tricks such as redundant encoding for numeric computation and memory addressing. Again, maybe you can imagine what happens. Don't stall speculation because the oldest instruction in the machine is a cache miss. Let the front of the machine continue executing branches for getting data dependent on cache misses. We talked about that already, actually, but this doesn't talk exactly about run ahead clearly. Okay, let's. I think I agree with a bunch of things over here. Remove small arbitrary limits on the number of cache misses outstanding allowed, for example. I think that helps clearly. But I would recommend you take a look at papers like this. It's very useful. So I gave this talk, actually. This run-ahead receives the Test of Time Award at HPCA, one of the major conferences in computer architecture. And I was kind of retrospecting, if you will. And I think this sort of issues are still critically important. And run-ahead is a microarchitectural technique, even though I believe it's not, clearly it's a compute-centric technique, right? It's not a memory-centric technique, but this has place in memory-centric systems also. One of the reasons I like talking about prefetching is it applies to compute-centric systems, but it also applies to processing in memory. So if you're doing processing in memory, you still need to have prefetching, unfortunately, because your latencies are long. If you don't have prefetching, or if you don't have some locality exploitation and prefetching, then you have a problem with even processing in memory. So this sort of techniques are very fundamental in the end. And this was actually a very good collaboration with Intel and us that continued for a long time and still continues now. And I believe fundamental problems will always remain fundamental. And they will require fundamental and increasingly creative solutions. So people need to come up with more creativity over time. Okay, and if you're interested, you can read the citation for the Test of Time Award. I think I like this one most, maybe over here. It spawned off a new area of ILP enhancing microarchitecture research because people were thinking, let's build large instruction windows. And then here comes a paper that says, let's not build large instruction windows, right? It's essentially a contrarian to the major way of thinking at that time. And as a result, some people follow, okay, maybe let's not build large instruction windows, let's do something else and let's explore what's going on over there, right? That's how research progresses, in my opinion. You don't necessarily do something everybody's doing. And if you see actually that people are stuck doing something, if there are some downsides, it's important to actually point out that there are some downsides to the approach and there's an alternative approach over here. Okay, and then you can read more, you can watch more. There's more, are there any questions? I spent more time than expected on run ahead, but we'll start multiprocessors at some point. I recommend more stuff on prefetching. Clearly, we had a prefetching lecture last week, which covered a lot of things, but there's a lot more actually we covered in the past. If you're interested, you can take a look at them. Okay, if there are no questions, I will briefly mention research opportunities because I think this is a good segue into research opportunities. If you're interested in doing research in any area, I think you should start as early as possible. I started as an undergraduate, for example, while I was at Michigan, and I learned a lot about stuff that I don't work on necessarily right now, but you build a lot of experience that way. But if you're interested in computer architecture specifically, we clearly have a lot of research going on. You've seen a lot of projects. Whatever you're interested in, internship, bachelor's, master's, semester projects, or even a PhD, then you should contact us. And you've seen a lot of these, so I'm not going to go through a lot of these. You will see some more. By the way, when we talk about interconnects, going back to your question, when we talk about interconnects, I will mention some things that we have worked on also, like bufferless interconnects. I recently discovered that some major company implemented the ideas in their system, and they exposed in a paper also. So it's good to see, basically, a paper that you write in 2019 or 2014. That was actually a long line of work, if you will. It gets implemented in a major company's processor. So it's good to see, basically, these things. Okay, so basically, you know a lot of these that what we're working on. I'm not going to harp on it again. And we take a very broad approach to the problem. I believe that that's really important. So RunEd is actually interesting because it was a very micro-architectural technique, but it's very, very hard to come up with techniques like that, in my opinion. If you come up with them, it's a great thing to research. But I think it's very difficult, and the field is becoming very much harder to improve things at one level. That's why we really need to improve things at multiple levels today. Processing in memory is an example of really all of these levels somehow combined together, right? Okay, and then there are a bunch of research. This is one slide summary of the research we do, and there are a bunch of links, but I think you've seen a lot of these, so I will not bore you with it. And we like open sourcing a lot of the research, and you can see that, as I mentioned, we talked about Ramulator. It's used by industry and academia. MQSim, another simulator used by industry and academia. And clearly RowHammer is over here, but some things are not even here, like the genomics works. I guess Sneaky Snake is here. Interesting. Okay. Yeah, and then you can read more about us. This is the newsletter from last year. You can read what people have been doing more recently. Clearly, we don't cover everything, but there will be another newsletter in December 2022, hopefully. And you can, I think we may have discussed this at some point, but a good way of learning about what's going on and research in general is this talk, and there are interviews as well. But you can also talk to me. Don't be afraid. So basically, this is a slide that I end up with. Talk with me, and also talk with other people who are doing research. Girai is here. He's doing research. Alsong is here. He's doing research, right? Yeah. Even when he's doing research, he asks questions about, for example, things. That's fine. Yeah, he submitted a paper recently, so he may be half awake. Right? Yeah, he looks like half awake. Okay, but basically, there's a lot of room for creativity, innovation, and high impact. And again, we just talked about some areas. Okay, any questions on this? Going once, twice. You can ask later also. Now let's switch gears and talk about multiprocessors. Now, multiprocessors is interesting, especially covering this after RunEd is interesting because RunEd actually brings up issues in multiprocessors also, right? Once you start prefetching aggressively. In general, prefetching and multiprocessors are interesting, and people have examined interactions. We have examined interactions, as you remember, right? It's important to design your mechanism not just for single processors. Today, everything's a multiprocessor, right? So it's really important for your mechanisms to work in the context of multiprocessors. Now we're going to delve a bit deeper into multiprocessors from a very basic perspective to begin with. And there are a bunch of readings I will recommend. We're going to talk about Amdahl's law. How many people know about Amdahl's law? How many people do not know about Amdahl's law? Don't be afraid. Okay, so good. You're going to learn something. I teach about Amdahl's law in digital design and computer architecture. I assume you guys have not taken digital design and computer architecture. Okay, yeah. Well, you can always take it online. But I'm going to talk about Amdahl's law clearly. What was I going to say? Yeah, we're going to talk about Mike Flynn's seminal paper. So you can see that these papers are from 1960s, and there are a bunch of good readings on multiprocessors. These are very fundamental readings. We're going to talk about memory consistency in the later part of this lecture. Hopefully, we'll finish it today. And then maybe next week, we're going to talk about cache coherence. And these issues are quite interesting, clearly. I mean, as I said, everything is multiprocessors today, and cache coherence is also going to change. Cache coherence is actually one of the toughest things that in the scaling of machines. You will see that when we talk about it. But let's jump into it. So this is a fundamental paper that provided a taxonomy of computers early on in the 1960s. I'd recommend people to look at it. But basically, there are two dimensions. One is the instruction dimension, whether you're executing single instruction or multiple instructions, or multiple instruction streams, let's say, and whether each instruction operates on a single data element or multiple data elements. Single data element meaning that you add a scalar data element, right? You add one value to another value, and then your result is a final value, right? That's considered a single data element. It's called scalar, basically. Whereas if you're operating on multiple data elements, it's really vector. You have a vector of elements or array of elements, and you're operating a single instruction is operating on many of them. So SysD is what we have been talking about in single-threaded processors, right? Single instruction operates on a single data element. You have this is just like an x86 machine today, right? Or ARM, without the vector extensions, of course, right? So modern machines are actually a combination of all of these. But SysD is in pure form as single instruction operates on a single data element. Like an add instruction operates on register 1 plus register 2, puts the result on register 3. These are all scalar elements. SIMD is basically each element is a vector. Essentially, a single instruction operates on multiple data elements. Whenever you specify a SIMD load, a vector load, for example, you also specify a vector length, or let's say vector add. Let's be simple. You also specify a vector length, and a single instruction can add two vectors, and the result will be a vector, right? So this is what how a lot of GPUs operate today. But existing processors like CPUs also have SIMD instructions inside them, right? Array instructions. For example, Intel has AVX extensions, and those extensions are essentially SIMD extensions. MISD is interesting. If you have taken digital design and computer architecture, you would have seen it. Systolic arrays are an example of it, but you have multiple instructions operating on a single data element. And this is kind of odd, of course, right? Multiple instructions, how are they operating on a single data element at the same time? Well, the point is it's not at the same time normally. You have one instruction transforming the data element to something else and outputting the data element into the next instruction. Next instruction doing something else to the data element and transforming and outputting into the next one. And basically you have a regular form, regular structure in the systolic array. And the closest form is systolic array for MISD. MIMD is what we're going to talk about basically. Here we have multiple instructions that operate on multiple data elements concurrently, and your program is written this way. Usually you have multiple instruction streams to be able to do that. A multiprocessor or a multi-thread processor and a multi-core processor is an example of this. Okay, so I'm not going to cover SIMD. SIMD example is vector and array processors, and modern GPUs actually employ both vector execution and array execution in existing incarnations. So that's an example. If we have time, we may actually go and cover SIMD, but probably we won't have time. We will recommend some lectures probably. But it's covered in digital design and computer architecture. You can watch it. And then there's a GPU lecture after this also, actually. There are two lectures that talk about SIMD. Systolic arrays, probably we're not going to cover them also because we've already covered them in digital design and computer architecture. These are actually the basis of a lot of machine learning accelerators today. So you can basically do systolic computation for matrix multiplication or matrix vector multiplication. And you can see an example of systolic array implemented in Google Tensor Processing Unit over here. You basically input data elements from the left, and the data actually flows through many, many instructions that are encoded inside this array over here. It's a matrix multiplication, basically. But again, I'm not going to talk about that. We've already talked about that. These are actually fascinating topics, I think. Systolic arrays were invented in the late 1970s, but they were not popularized until the machine learning accelerators, until they became machine learning accelerators about 40 years later, basically. I'm a bit proud because I teach. I've always taught systolic arrays since I started teaching, because I always thought that these are clearly important and fundamental, and they're going to have their use cases, big use cases in the future. So you can go and see my lectures from 2011, 2012. They have systolic arrays in there. So it's good to basically teach fundamental things, even though they may not be popular at a given point in time, right? Popularity has nothing to do with, let's say, the importance of an idea, I would say. Keep that in mind. Okay, so let's be even more fundamental. Let's talk about why parallel computers. So parallelism means, at the very basics, doing multiple things at a time, right? And this can be applicable not just to computers, clearly, humans and everything in the world can potentially do multiple things at a time, right? And we have a lot of parallelism clearly in nature, right? Things in case of computers, things can be instructions, operations, and tasks. What is the original goal of this? Why would you ever want to do multiple things at a time? Anybody? Efficiency. What does that mean? Okay, performance. I like that. Yeah. Basically improve performance. Basically you improve execution time or task throughput. Okay, yeah. Now you're giving 2 reasons. Okay, let's see. There are other goals basically. I think what you guys are getting at is that, right? What are the other goals? Complexity, basically to make things simple. What else? Maybe efficiency. If you have resources, don't let them go utilized. Maybe it's similar. Both of those are similar. What else? Okay, that's good. Yeah, that's one of those. You can see there are a bunch of things that are going to come here. I'm not going to have sub-bullets. Maybe there are sub-bullets. Reducing power. Yeah. What else? There's okay, yes. Okay. You mean in terms of performance? Energy? Okay. Okay. Yeah, they'll better utilize the memory, maybe. Yeah, similar to her argument, I would say, efficiency. Yeah, I mean, that's true. What you said is true, but it's I'm looking for something more fundamental. Like, what does it improve fundamentally? There's something that's missing that no one has said so far. Okay. Okay. Yeah, but I think they come with performance, etc. Right? Why do new workloads appear? Why did machine learning become so popular? Because GPUs were so high performance, right? That's the reason. I think these are effects. These are effects of these other goals that people have been trying to optimize. There's one thing we discussed early on in the lectures. Why would you duplicate a resource? If your goal is not performance, efficiency, complexity, you don't care about any of those. But I just want to duplicate the resource. No? Because I don't rely on this resource. Maybe, yeah, okay. Okay. I see. That's right. But that goes back to, I think, efficiency arguments. So I think I would club them into efficiency, scalability, cost efficiency, etc. But what I'm getting at is, okay, sorry. Okay, I'll do all of this. Improve dependability. Basically reliability, right? Remember the bridge that we showed? Yeah, one version of the bridge that goes down. Okay, there's another bridge that already operates, right? That's the idea. And this is very fundamental. This is one of the reasons why people actually improved parallelism in early machines, early in 1970s, because one of the processors had an error. Okay, you have another processor that executes the computation, right? So end modular redundancy is an example of this, basically. And this is applicable to any resource, not just the processor, clearly. But the other things that you guys have already said, like these things, these two things actually have really pushed people to move from single core to multi-core recently. But reducing power consumption, for example, is a good reason. If you have, for example, 4 N units at frequency f over 4, you can consume much less power than N units at frequency, each at frequency f, right? This clock frequency. Why? Yes. With frequency, right? Yeah. Actually, I'll just write it, I guess, if I can find the. Let's see how we switch to this. Does anybody remember? I have a tough time remembering. I think what do we do? Blinds, ventilation, no. Device, okay, device. Okay. So power consumption. But can you see it? I guess I stopped sharing. It's a bit annoying to do that all the time, but yeah. Okay, power consumption is equal to capacitance and voltage square F. And basically, voltage is also, I guess, correlated with F. So really, what you do is, if you want to reduce power consumption, you reduce frequency, which means that you can also reduce voltage quadratically. So power consumption is really this dynamic power consumption is really cubically related to power. So you can reduce power consumption in a cubic manner if you reduce frequency. So that's why I should say that this dynamic power. There's also a static power consumption that is independent of frequency. Clear, that's really dependent on the leakage that you have. But if you have very high performance circuits, that leakage also may increase because you need high performance circuits to operate them at high frequency. So this is the reason why I can reduce power. And this is actually one of the scaling laws. Unfortunately, this doesn't work very well in today's regimes. I mean, this is power consumption law, but basically this scaling of when you reduce frequency, you can also reduce voltage significantly. Doesn't work very well today because we're already at very low voltage levels today. And you cannot push the voltage even lower because you run into reliability issues, basically. So we're having trouble with the power consumption aspects because of this today. And if you want to learn more about this, called Dennard scaling. And Dennard actually has discussed this scaling laws. And it really builds on the fact that you can reduce frequency and also reduce voltage at the same time. Okay, so that was a quick discussion of power consumption. No? Now let's go back to sharing. But that's essentially what parallelism buys you. Parallelism enables you to, no, I don't want to leave the meeting. Parallelism enables you to have more processors operating at lower frequency, right? And here I basically said 4 times the processors operating at 1/4 the frequency. Now, this is of course assuming there's an assumption over here that you parallelize your program perfectly, right? Yeah, this assumption is really important. Don't ever forget that. And we will see that that's not always the case. And we will see that parallelizing your program perfectly is actually a very difficult task. So don't forget that assumption. Even if that assumption is not perfectly true, you can reduce your power consumption because of that cubic relationship, right? You reduce the frequency a little, and you get actually a huge reduction in power consumption, assuming it still holds. So even if your program is perfectly parallelizable, you can still get the benefits of power consumption. But ideally, if you don't lose performance and reduce power, and that was the goal essentially with multi-core. And then we've also discussed improved cost efficiency, scalability, reduced complexity, all of these things that you guys threw. They're all correct. Basically, it's harder to design a single unit that performs as well as n simpler units. And there's no good way of expressing all of those at the same time, but I think of those as very related to each other. Okay. Okay, so now let's talk about how do you actually exploit parallelism. These are different types of parallelism that are exploited in modern systems: instruction level, data level, task level. Instruction level parallelism is exploited in out of order machines, for example. Different instructions within a stream can be executed in parallel, right? So it's a single stream, but you're executing in parallel. Pipelining is an example, actually. Simple pipelining is executing different instructions in parallel in different stages, right? Out of order execution, speculative execution, VLIW, data flow. We will discuss data flow a little bit more. Makes sense, right? Data parallelism is different pieces of data can be operated on in parallel. This is the single instruction, multiple data paradigm. Vector processing, array processing, GPUs, systolic arrays. Also, MISD is another example of this, actually, in a different way, let's say, because you actually do multiple things in MISD. But these are actually exploiting data parallelism. And then there's task level parallelism, which is essentially what we're going to talk a lot about. The different tasks or threads can be executed in parallel. This multi-threading and multi-processing, essentially. And these different tasks can be cooperating, or they could be completely independent, as we also discussed earlier. But existing machines are a combination of all of these, actually. You can have GPUs are, for example, exploiting task level parallelism, thread level parallelism, as well as data level parallelism at the same time, and somewhat instruction level parallelism in the compiler. But you can think of all the machines are combining these things in different ways. So let's talk about creating tasks. We've already discussed this, so I'll go through this relatively quickly. But one way of creating tasks is relying on someone submitting the task, run many independent tasks together. But we also discussed partitioning a single problem into multiple related tasks. This is called threads, multi-threaded programming, basically. If you do this explicitly, this is parallel programming. The programmer does this. And this is usually easy when the tasks are natural in the problem, easy in quotation marks, because in general, parallelism is harder than single thread, clearly, right? Because you need to think more think about more things to handle, especially when they synchronize, which we're going to talk about a lot. But for example, complete independent database queries are one example. But difficult when natural task boundaries are very unclear, right? If you have a single program that is doing something, it's complicated. How do you parallelize it? Yeah, we'll talk about that maybe later. This is explicitly done, right? But you can also do this transparently, implicitly, either in the system or the or the compiler or the hardware. And now this is called thread level speculation or thread level parallelization. Usually these techniques are speculative. They're not completely, let's say, parallelizing the program because they don't know some things. So you need to be speculative. And the idea is to have a single thread. The programmer writes a single thread and the compiler or the hardware partitions it. Okay, we've talked about this a little bit, right? When we talk about speculative pre-execution. You could have a thread generated for speculative prefetching, but that thread can also compute results. And now you need to actually merge the results to the main program, right? That becomes tough, of course. Usually this is, the efforts here have been not as successful, as I should say, compared to parallel programming. Parallel programming is tough, but people are doing it today because that's how you gain performance, right? And then run many independent tests or processes together. This is multi-programmed workloads. Clearly, this is relatively easier compared to that one, assuming you have them. Easy when there are many processes, batch simulations, different users. Cloud computing relies on a lot of this, clearly. But it doesn't improve the performance of a single task. So we're going to focus a lot on improving the performance of a single task in these lectures. We've focused a lot on this one earlier. It's still important, but it's not as difficult as the first one. So let's jump into a little bit fundamentals. Feel free to ask questions, by the way. I'm going through this, but these are relatively basic. So there are two major multiprocessor types. We're going to talk especially on the about the second one, tightly coupled multiprocessing, because loosely coupled multiprocessors are everywhere, essentially. The main distinction between these two things is from a programming perspective, do you have a shared global memory address space? So different threads that you write, do they share a single global address space such that whenever you do an operation on one memory location, the other thread can see it? Right? In loosely coupled, that doesn't exist. That's why they're called loosely coupled. They have their own private memory address spaces, these different processors. In tightly coupled, there is a shared global memory address space. That's why these are also called shared memory multiprocessors. Okay, so the first one, a great example is a multi-computer network. Essentially, you have a multiprocessing system over here, and you can program them to execute a single task in parallel. Not a lot of people do it, but actually people also do it. If you know what you're doing, you can do it basically. These are network-based multiprocessors. This is more traditional, clearly, traditional multiprocessing. It's also called symmetric multiprocessing. I don't like that terminology because it doesn't need to be symmetric. But basically, existing multi-core processors and multi-thread processors all have shared global memory address space. So the first type of multiprocessors, because you don't have a shared global memory address space, whenever you communicate between processor 1 to processor 2, you need to send messages. Usually, they are programmed using message passing. I say usually because it's not always. You can actually play tricks, but usually this fits. So you basically use explicit calls, send and receive for communication. This is like networking, essentially, right? If someone produces some result, you basically send it. And then that particular processor takes it from the network and puts it into its memory, and then you can do loads and stores. Whereas in tightly coupled multiprocessors, you don't need to do that. Programming model is very similar to uniprocessors. That's why these have been easier, let's say, to program. So you can basically do loads and stores. Every thread can do loads and stores to any part of the memory that's visible to programmers. Except the difference here is your operations on shared data require synchronization. So if you want to actually communicate between two different threads that are running on different processors, you need to somehow do some synchronization. I mean, you can do a load and store clearly, but we will see that that may actually lead to problems. I mean, even synchronization is implemented using load and store instructions in the end. Does this make sense? Okay, so hopefully this is simple. You may have seen it. How many people have seen this difference before? How many people have not seen this difference before? Okay, okay, good. And if you have questions, please ask. Okay. But I think the way to think about it is it's a multi-computer network is really a loosely coupled multiprocessor, whereas whatever I have over here in my multi-core machine is a multiprocessor. I mean, even this is a multiprocessor, right? Because they have shared memory address space. But it doesn't have to. Internally, it doesn't have to have a shared memory address space, right? So physical shared memory address space is different from the programming level shared memory address space also. Keep that in mind. Okay, so there are a bunch of issues in tightly coupled multiprocessors, and we're going to see a bunch of these. How do you synchronize? How to handle synchronization, locks, atomic operations, barriers, the things that we have seen earlier. We're going to briefly discuss that. But we're not going to, this course is not going to be about parallel programming or synchronization. If you take a parallel programming course, you will talk about synchronization. We will assume that synchronization implemented in some ways, but we're going to support it in the hardware and system stack. Cache coherence, how do you ensure correct operation in the presence of private caches keeping the same memory address cached? We're going to talk a lot about that. Today, we're going to hopefully talk about memory consistency. What should the programmer expect the hardware to provide in terms of the ordering of memory operations? We will see that there has to be some basics. Otherwise, you cannot get correct operation of multiprocessors. We talked a lot about shared resource management. And then we will later talk about communication, and interconnects are going to be important. And we've talked about load imbalance. How do you partition a single task into multiple tasks? How do you synchronize efficiently between tasks? How do you communicate between them? What are the synchronization primitives? Again, these are not some things we're going to focus a lot on. Contention, avoidance, and management. We've kind of seen this. This can happen in hardware and software levels, basically. In the hardware level, we talked about contention for memory, for example. In the software, there could be contention for locks, right? And they may have hardware level effects. How do you maximize parallelism? That's going to be important. And how do you ensure correct operation while optimizing for performance? We're going to talk a lot about this, actually. First, you need to start with correct operation, actually. That's what we're going to start with. So I should also say that multiprocessing and multithreading, they're very similar to each other in the end. It's basically a matter of granularity. Multithreading, clearly, you have a single processor, but you have multiple threads that you can concurrently run over there. Multiple instruction streams can concurrently run. And this could happen in a slightly coarser grained manner. For example, quantum-based, every 1,000 cycles, one thread runs, and then you switch to another thread context after that. Or you switch based on an event. Like run-ahead is an example, except you don't switch to a speculative thread, but you switch to another real thread that is in the program. And these are all implemented in real systems. You can do fine-grained cycle-by-cycle switching. Every cycle you fetch from another thread, for example. Or it could be even finer grained, this is simultaneous. In an out-of-order machine, you can simultaneously dispatch from instructions from different threads at the same time. Right? Here you fetch from a different thread every cycle. Here you can basically, in the execution, you can parallelize different threads at the same time. And clearly, these are actually good for improving utilization. All of these are good for improving utilization. We will not talk a lot about multithreading. There are a bunch of lectures. Again, if you took digital design and computer architecture, you've seen fine-grained multithreading. But there's a lot more on multithreading, which I'm not going to cover. It's actually a huge topic. I think at some point, this was in 2012, we had 4 lectures or something on multithreading. But that was a different course structure while I was at CMU. Yeah, we could go deeper, let's say, in some of these topics. Okay, so if you're interested in that, you can take a look at that. You can clearly see that there are 4 different lectures over here. Okay, any questions? Now we're going to have some fun talking about parallel speedup. I'm going to ask you some questions. Let's see. So get ready. So, okay, I have this nice polynomial evaluation over here. Maybe not written as nicely. It's not that bad. But basically, this is a polynomial evaluation, right? This is A's are constants, X's are variables. Let's assume that we have a program whose sole task is to evaluate this polynomial. You assume X and each AI. These are the inputs. You assume each operation takes 1 cycle, multiplication or addition, and those are the only operations you have here. Clearly, A4 X to the 4 means that you have, 5 multiplications over there, right? Because X times to the 4, how do you get there? X squared, X third, X fourth, yeah. and then you multiply by A. That's 5 multiplications, right? But this is basically what we will assume. It will be very simple. No communication cost. We're not going to even communicate between different things. Each operation can be executed in a different processor. So each operation, each addition or each multiplication can be executed in a different processor. Now the question is, how fast is this with a single processor? You can start thinking about it. I'll ask the other question. Well, let's say assumptions. The assumptions are no pipelining or concurrent execution of instructions, basically. Simple. Each instruction finishes in 1 cycle, basically. But you can parallelize them. You will see that you're limited by data dependencies in the end. And then the next question is, how fast is this with 3 processors? Oh, okay, let me not go there. Maybe I'll take some. I mean, you can. There are smart people who can do this in their heads. I have to write it down. But maybe you're one of those smart people, or write it down, up to you. But I want answers. I would like you to answer how fast is it with a single processor versus how fast is it with 3 processors. We're going to talk about infinity later on. Any thoughts? How fast is this with a single processor? You have a single processor. It can do 1 operation per cycle, and it finishes one operation, hopefully every cycle, right? And there are a lot of operations here. Anybody? Yes. 12 cycles. Okay. Any other takers? I'm not going to say yes or no. We'll see the answers later on. You can change your answer if you want. Take this as a hint. Okay. Now he's thinking. Anybody else? Come on, he's not the only brave one. 15, okay. 11. That's what I would begin with, probably. Sorry, guys. How you can reconsider your answers. What else? Anybody? Don't worry, that's not an exam question or anything. I'm not evaluating you. And everybody makes the same mistake in the end. Except sometimes people think deeper. And anybody else? Okay, who says 12? You're sticking with your answer? No, okay. Who says 15? Single processor, yeah, we were just talking about the first question. How fast does it take with a single processor? With these assumptions, of course, right? No communication cost. Well, in the single processor, it doesn't matter, communication cost. But okay, no other takers? You have? $17, okay. Okay, maybe I tricked you. You're inventing some operations over here. So basically, okay, let me say it this way. This is not a to the power 3. It's a constant. A3. Okay, I think you're counting as a to the power 3, right? That's not a to the power 3, no. It's a constant over here. So for example, a1x requires 1 multiplication, multiplying a1 and x. And a0 clearly doesn't require any operation, but adding it to something else requires 1 operation. Okay, let's answer this for, how many people say, yeah? 12, okay. So, okay, 12. 11. I think we're converging somewhere between 11 and 12, yes? 9, okay. Somebody's improving performance. That's how progress happens. Okay. So who says 12? Who says 11? More people. Okay, who says 9? Who says none of the above? I mean, it has to be something. Okay, so basically 11 cycles. This is what, basically if you draw the data flow graph of this is how I would draw, right? A1 times x, and then I compute the x square. And this is a single processor, right? Basically, it doesn't matter. This parallelism, don't worry about when things are executed. Everything is executed serially. But you can compute A1x, and then x square over here, and then x cube over here, x to the power of 4th, and then this is A4x4, and then this is A2 x square, and then A3 x cube over here, and then add to it A4x4, and then add to that sum A2 x square, and then add to that sum A1x over here, which you computed, and then add to that A0. So it's 11 operations, basically. If you have 11 operations and every single operation takes 1 cycle, you have 1 processor, it should be 11 cycles. Right? So people who said 11 are correct. Okay, free processors, I think I'm going to give it to you because it requires some hand stuff to do it. You basically get 5 cycles. Because now we were assuming 3 processors. What you do is basically you can take that data flow graph and parallelize it. That's one way of doing it. Or you can think in some different way, right? But basically, in the first cycle, you can compute these things in parallel in 3 processors. In the second cycle, you still have 3 operations. 3 processors are doing the next operations that are dependent, clearly, as you can see. We're assuming no communication cost. So the edge from here to here costs nothing for us, which is a not realistic assumption, clearly. An edge from here to here and here to here doesn't cost anything. And then in the third cycle, you have 2 operations. In the next cycle, you have one operation. In the next cycle, you have 1. Because you have dependencies, right? So 3 processors takes 5 cycles. Make sense? Okay. So speed up with 3 processors is essentially 2.2. Does that make sense? So if someone asks you to compute the speed up is basically how long it takes with 1 processor divided by how long it takes with 3 processors. I mean, you just said 11 divided by 11 and 5, 2.2. Not bad. You put 3 processors to the problem, you get 2.2x speed up. Does that sound good? Everybody's okay with it? Okay. Now the question is this a fair comparison? Well, of course, given the assumptions, right? If you had a communication cost over here, this could actually easily take much longer, but we're ignoring that. Anybody? So if 9 is right, this is not a fair comparison, right? Basically, it should be 9 divided by 5, which brings you down to 1.8. So you're throwing 3 processors at the problem, and you get 80% speed up. Now it's not sounding as attractive to have 3 processors, right? Ideally, you want 3 processors and 3x speed up, right? But if she is right, and she is half right, actually, but that's not the best you can get. I'm sure you can get this in 9 cycles. Yeah, 9 cycles in a single processor, sorry. But I think you can do even better. Okay, so let's revisit the single processor algorithm. And if you want to revisit it, I recommend you read Horner's 1819 paper that talks about Horner's method of evaluating polynomials. And basically, we're going to be a bit smarter on how we look at the polynomial. And we're going to basically, do this essentially. And this is called Horner's method. You may have seen this in high school. How many people learn about Horner's method in high school? Okay. How many people do not know about Horner's method? Okay, some people may not learn. But maybe you forgot it. Now you remember Horner's method. This is where you see Horner's method again. In high school, people may not motivate why this is important, but this is why it's important, basically. You optimize algorithms in the end. But basically, if you use Horner's method, you will immediately see that actually leads to a very small number of operations, right? You basically do this multiplication first, 1 operation, addition, 2 operations, multiply, 3 operations, 4 operations, 5 operations, 6 operations, 7 operations, 8 operations. So maybe you miscalculated 1. So you basically can reduce what I showed you earlier to only 8 operations. And in a single processor, it will take 8 cycles, basically. And your speed up has gone down even lower. It's 1.6 now, not 2.2. So I think this is a very fundamental example to see how important it is to optimize algorithms, right? And also how important it is to keep your high school knowledge, but maybe high school needs to be more geared towards like, why is this important as opposed to, okay, this Horner's method, this is how you evaluate polynomials and good luck with it. Yeah, I think this is, I mean, clearly I realize it backwards also, right? When I really started studying computer engineering, you really appreciate some of the things that is done in math classes, because that's really what these methods feed you. Of course, there's a fundamental benefit to this sort of methods in mathematics, but there's an applied benefit to these methods also, as we can see over here. So basically, what happened was, if you have a bad or poor single program or single thread algorithm, you may think your multiprocessor is great, 2.2x. But in the end, someone can come up with a better single processor algorithm and your multiprocessor may not be that great. Right? So it's good to think about it this way. So it's in the end, you really need to optimize your algorithms and hardware. And in fact, you can get superlinear speed up also. And this has been reported in the past, including in scientific papers. you should always question things when you see things like this. Can speed up be greater than P with P-processing elements? Basically, you can look over here, number of processors. This is called a scalability or speed up curve. Number of processors on the x-axis, parallel speed up on the y-axis compared to a single processor. Linear is over here. Typical success looks like this, but sometimes people report speed ups that are super linear. With 5 processors, you get 10x speed up. If you hear that, you should immediately raise the alarm bells. What's going on here? Now, usually what's going on is one of the two things, unfair comparisons. Basically, they may compare best or good parallel algorithm with a wimpy serial algorithm that they didn't optimize. And this is very unfair in the end. It pollutes, let's say, a lot of things. Of course, it'll be figured out at some point by some smart people, assuming the problem is important. So this is clearly a no-no, right? This is unfairness is not good. But sometimes people may not know the best serial algorithm also, so that's also interesting. Some unfairness may not be malicious necessarily, right? Unfairness may be because there is not enough knowledge on this topic, and people may not have invented the best serial algorithm. So it's good to think about it that way. Usually it's people are overly excited about, oh, I have this best parallel computer. Now let me compare it to this algorithm that I find without thinking about, oh, is this the best serial algorithm? And then they report results. And then that kind of inflates the importance of parallel computers, let's say. Usually that's the case. Because there's usually someone who knows the best serial algorithm. If you actually search enough for it, you'll find it. Okay, but not always, as I said. And then there's a real effect, which is not because of unfairness, which goes back to memory and cache. And people, a lot of the times, forget about this, which is more processors. When you actually add more processors, you're also adding more cache and memory in general. And the benefits are really coming from this. You get fewer misses in aggregate in your program because you have more cache and more main memory, or fewer page faults. And then you can get super linear speed up. In fact, your speed ups can be huge over here, because imagine you have one processor, one processor, 1 megabyte of cache, right? And your program keeps missing. And then you basically parallelize it. You have, 128 processors, 128 megabytes of cache, aggregate, because each processor has 1 megabyte of cache. Now your entire data set fits in all of the caches. You never get a cache miss. The performance improvement is not coming from the parallelization that you did. It's really coming from the fact that you've added more cache and you're not going to memory as much. Well, you're not going to memory in my particular example, right? So this is real. This effect is completely real. It's not necessarily unfair because you're not really unfairly comparing algorithms, but you need to acknowledge this basically. It's not coming from parallelization basically. So a lot of supercomputers actually benefit from this effect. People design these supercomputers that do a lot of stuff. Sometimes the reporting is such that, oh, we have all these computers, but they forget the memory. Well, there's a lot of cache that you're adding and memory you're adding. And that's one of the major reasons why these performance is improving, actually. Okay, so keep that in mind. I think these are important fundamental slides, if you will. Any questions? Anybody came up with a better algorithm than Horner's method? Then you can publish it in where Horner published, if it still exists. Okay. Okay, so I'm going to very quickly define these metrics. These are interesting, but kind of boring also. Basically, they're traditional metrics to evaluate multiprocessors with. You're assuming all P processors are tied up for parallel computation, for the amount of time the computation is done. So you have a P multiprocessor, and all of them are tying up. Utilization is how much processing capability you're actually using. Basically, it's number of operations in the parallel version divided by the processors you're tying up and the time you're tying up the processors for. I'm going to give you an example with the previous example earlier. Redundancy is how much extra work is done with parallel processing, and you almost always do extra work with parallel processing, even with the assumptions that we've seen. Usually there's extra work because you need to communicate some data from one processor to another processor. Sometimes you actually need to replicate the data so that you can parallelize. So basically, redundancy is number of operations in the parallel version divided by number of operations in best single processor algorithm version. Remember, these are best. Best is very important, otherwise you can get really weird numbers over here. Okay, efficiency, what we have discussed earlier, is the time with one processor divided by number of processors you use and the amount of time you tie them up with parallel computation. And efficiency turns out to be U divided by R, utilization divided by redundancy. It's interesting. It's fun to look at, but in the end, they don't mean a whole lot in today's world, because in today's world, we really care about energy efficiency and performance. These are some metrics to see how efficient you are. So it's good to look at it sometimes when you're optimizing things. So utilization basically is how much processing capability you use. If you think about it, we're tying up 3 processors for 5 cycles in the previous example, in the multiprocessor version. And how many cycles are actually spent on executing something in each of the processors? And if you actually look at what we have done in the earlier data flow graph in 3 processors, X's are the slots that you utilize. Basically, we have 10 operations in the parallel version, but we're tying up 3 processors for 5 cycles. We could have executed 15 operations. So our utilization is 10 divided by 15, basically, 2/3. Redundancy is how many operations we have in P processor version divided by how many operations we have in 1 processor version. It's 10 divided by 8. If you didn't optimize the single processor version, you would get 10 divided by 11. And that should immediately raise alarm bells. Does that make sense? If you're having 10 operations in the parallel version and 11 operations in the single thread version, you're doing something wrong. So that's one way of spotting that you're doing something wrong, an unfair comparison, basically. That's the benefit of these metrics, actually. I said these metrics are not necessarily beneficial, but if you are not doing things right, these metrics can be very useful for you to understand what's going on. Yes, you can press the button also.
I think here you mentioned how much extra work. So it should be 2 divided by 8, not 10 divided by 8, right?
No, actual work is how many real operations you're executing. I don't know where you get the 2 from, but 10 is the number of operations we executed in this version. Let's go back over here. Yeah, this is 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Does that make sense? In the multiprocessor version, we have 10 operations. In the best single processor version, we have 8 operations. Okay.
How do you define extra?
So extra is basically a 10 divided by 8. It's 25% in this particular case, assuming that we've got the best implementations of the algorithms. Okay, and then efficiency is how much resource we use compared to how much resource we can get away with. And this is basically, you have 1 processor and you're tying it up for TP time units. Okay, I don't know, T1 time units, sorry. That is 1 processor time units, that's 11. No, 1 processor was 8, right? 8 time units. As opposed to you have 3 processors and you're tying them up for 5 time units each, that's 15. That's 8 divided by 15. That's our efficiency, basically, which is a little bit above 50%. But you could also compute efficiency with U over R, so you don't need to compute it this way. Okay, now let's go into something also fundamental, Amdahl's law. So if you haven't seen Amdahl's law, this is Amdahl's law. I think I'll finish it. We'll take a break after this, let's say, lecture. We'll be done with Amdahl's law. But basically, Amdahl's law specifies the speed up, expected speed up. And it's a very simple formula that has only 2, let's say, inputs. The parallelizable fraction of the program, F, sometimes it's called P or alpha, and N is the number of processors. And this is the formula, basically. Your speed up is this. There is a parallelizable portion of the program. It gets divided by N. And there's a non-parallelizable portion of the program, which is 1 minus F. And then your speed up is basically 1 divided by the sum of this. So we'll derive this later on, but you don't need to even think about it. If you think about it, if your parallelizable portion is, let's say, 100%, ignore this. This is 1, and you divide by N. And if N is 10, you can completely parallelize it, your speed up is 10. Right? If your parallelizable portion is, let's say, 100%, which is 1, your speed up is essentially N, if you think about it. Again, this is assuming something. This is assuming that you can perfectly parallelize your program. Does that make sense? And this doesn't need to be applied to processors. This could be applied to anything, right? If there's some important bottleneck that you have, it's taking, I don't know, a fraction of the time, F. If you can speed it up by N, this is the speed up you're going to get. Maximum speed up. Why maximum? Because this is assuming that you can perfectly speed up by N. So it's not just applying to programs, it can apply to any bottleneck you have. It may be an energy bottleneck, right? You have some part of your, I don't know, system consuming 50% of the energy. If you perfectly get rid of it, what is the energy improvement you will get? 2x, right? Amdahl's law says 2x. Why? F is 50%, 0.5. So 0.5 divided by n. I'm assuming n is infinity because I can perfectly get rid of it. So this part becomes 0. This part is 1 minus 0.5, which is 0.5, and 1 divided by 0.5 is 2. So if you have a bottleneck that's consuming 50% of something, energy, performance, even if you perfectly get rid of it, the maximum benefit you're going to get is 2, which is kind of sad. Right? So this also implies that the bigger your bottleneck is, the more important it is to optimize it. And the more bang for the buck you're going to get, probably, assuming everything else is equal, right? So if something is consuming, let's say, 99% of your time, the maximum speed up you're going to get is 100, right? Because you get rid of 99%, what remains is 1%. 1 divided by 1% is 100. That's the idea. So that's the beauty of this, and the beauty and the power of this law. But basically, there are multiple ways of looking at it. I've already looked at it in multiple ways, but one way of looking at it is maximum speed up is limited by the serial portion. So if F is not perfectly parallel, F is not 100%, F is not 1, in other words, your maximum speed up is really by 1 minus F. Assuming that you can get rid of F over N by throwing more processors at it. We're going to see that that's not also easy, right? But that's the assumption we're making. And that's why Amdahl wrote this paper out, actually. He basically said that we're designing these multiprocessors, but look, you're going to be limited by the serial portion. You're going to be limited by what you cannot parallelize. And then he basically, you can see the title, right? Validity of the single processor approach to achieving large-scale computing capabilities. He basically said we should keep investing on single processors. You can read that in his paper. It's a very beautiful seminal paper. Some people argue that Amdahl's law doesn't exist. Ignore them. It always exists because it's so fundamental, right? I've seen actually people, I don't know what they're thinking, but they argue that Amdahl's law doesn't exist. How is it possible that something like this doesn't exist, right? It's all about bottlenecks, right? Basically, if you cannot perfectly get rid of something, you're going to be limited by what you don't get rid of. Let's put it in layman's terms, right? Ignore all of the parallel programming stuff. If you cannot perfectly get rid of something you don't want, you're going to be limited by what you did not get rid of. Okay, you can apply this to many, many things, I think. Okay, so that's what serial bottleneck is essentially. And this has actually been very powerful. It exists, and it really limits parallel speed up. As I said, okay, let's take F equals 95%, 0.95. The maximum speed up you can get is 20, regardless of however many processors you throw at the problem. That's, again, very sad, right? So you really need to parallelize your program extremely well, more than 95% to get a more than 20x speed up. Okay, so again, I've already said a lot of this, but this is why you have this reality also. This is a scalability curve, speed up curve. You have, as you add more processors, you get some speed up. And the reality looks like this. Speed up tapers off because you have diminishing returns, basically. Basically, you keep adding more processors. As you keep adding more processors, you're reducing this portion, but this portion is not changing. So the additional benefit you get by adding one more processor is not helping you as much, right? If you look at this equation, right? As a fundamental mathematical equation, as you increase n by 1, if n is very large to begin with, you're not going to get that much benefit because you're limited by 1 minus f. If you really want to get equal benefits, meaning linear speed up, you got to get rid of 1 minus f. So your f should be 1. Then, if you increase m by 1, you're going to get linear benefits, right? So that's the idea. So that's why Amdahl's law is very powerful. Even if that f is 0.00001, you're in trouble, basically. You're limited by 1 minus f. Okay, so this is the derivation of Amdahl's law, but you can do it by yourself, essentially. This uses, instead of f and n, this uses, what is this? Alpha and p. That's another way of thinking about it. But basically, the speed up as the number of processors goes to infinity is, so let's go back to what we're used to. As n goes to infinity over here, this term, f over n disappears, and the speed up becomes 1 minus 1 divided by 1 minus f. So if you plot this, these are the curves you get, basically. So this is this is the number of processors, this is speed up, this is one processor over here. They all start at the same point. And these are different parallelizable fractions, 90%, 95%, 98%. They all converge similarly in the end, right? So adding more and more processors gives less and less benefit. And the benefit is small until the parallelizable fraction is very close to 1. Okay, these are my quick hand drawings. If you don't believe me, oh, okay, sorry. Let's go. Let's see. If you believe Excel, this is what Excel does. This is the parallel fraction, from 0 to 1. Where do you get huge benefits? When you're very close to 1. Before that point, yeah, not that much, right? You're lower than 10x. And you know where exactly will be 10x with Amdahl's law at 90% point, right? So that's why Amdahl's law is very strong and very sad. Okay, this is the sequential bottleneck. So why do you have the sequential bottleneck? Essentially, you have non-parallelizable operations on data. Examples like this, non-parallelizable loops. Single thread can prepare data and spawn parallel tasks. Usually it's illustrated this way. You have a sequential thread that's just preparing something, doing something, aggregating data or spawning tasks. And then you have a bunch of parallel threads that run in parallel. And then you aggregate the data back in a single thread, and then you prepare the next task. You can see that these parts are sequential, right? This is sequential, this is sequential, this is sequential. And you can immediately see that the longer they are, the less benefit you'll get from parallels, because only one processor is executing them, right? You need to either parallelize them or find some other solution. So this is a real example. I will not go through this. We're going to talk about this paper later on. But for example, this stuff, all of this stuff, A, marked A, is serial. All this stuff marked E is serial. And here there's parallelism. But we will see that there are issues over there also. So this is the sequential bottleneck, A and E over here. Single thread is executing programs. This is the parallel portion. Ideally, the parallel portion, you should be able to speed it up as you add more processors. But as we have seen before, and as we're going to see again, there are bottlenecks in the parallel portion also. And that's what Amdahl's law doesn't take into account. Let's go back to this Amdahl's law. So basically, Amdahl's law takes into account the serial bottleneck. That's the only thing that it takes into account. It doesn't take into account parallel portion. It doesn't take into account the fact that it's not perfectly parallel, because it basically divides F with N, right? It doesn't consider that there's other stuff going on. And we've already seen that there are problems in the parallel portion. I'll just mention them. These are very fundamental also. There's synchronization overhead. The threads are synchronizing with each other. And whenever one thread needs to wait for another while synchronizing, you're basically, that F divided by N is wrong, because you're causing waiting and you're not executing something in one processor in that case, right? So synchronization overhead is one example. Load imbalance overhead, basically, Amdahl's law again, that's F over N, assumes that you perfectly parallelize your program. But what if one thread has a lot more execution time than another thread, because the programmer did not balance the program? That way, again, F over N goes down the drain. So even F over N, we're deconstructing it now. And then we've seen the resource sharing overhead. You have contention among multiple threads. One of them gets delayed significantly. Not the programmer's fault. The system designer may have designed that way. Again, F over N goes down the drain because you're not perfectly parallelizing across the threads. So basically, Amdahl's law just focuses on the serial bottleneck, but we're going to focus a lot more on the parallel portion also later on. Okay, I already said these. So bottlenecks in the parallel portion, we've seen these, so I'll go through this relatively quickly. Essentially, you have synchronization operations, and operations manipulating shared data cannot be parallelized. We've seen locks, mutual exclusion, and barrier synchronization. I'm going to show them very, very quickly again. But this is also communication essential. Tasks may need values from each other. That's why they need to synchronize. Right? And this essentially limits the parallelization that you can get with multiple processors in the parallel portion. Load imbalance. Parallel tasks may have different lengths due to imperfect parallelization or microarchitectural effects. And this reduces speed up in the parallel portion clearly. And resource contention, parallel tasks can share hardware resources, delaying each other. Replicating all resources is expensive, as we talked about earlier, much earlier actually. And this leads to additional latency not present when each task runs alone. Again, it reduces your parallelization. And we've already seen the slide actually. Basically, threads in a multi-thread application are interdependent and they synchronize with each other. Some threads can be on the critical path of execution, some threads are not. And within a thread, some code segments may be on the critical path of execution and some are not. We've actually seen this slide earlier when we talked about parallel application memory scheduling for example. But basically, this shows that what really matters is your critical path, right? That's divide by n doesn't work. Okay, so we've seen critical sections. I'm going to go through this relatively quickly because we've actually seen that in an earlier lecture. This is just to jog your memory. But this is one of the reasons why parallelization doesn't perfectly work, right? If these are the two parallel threads, right, T1, T2, and you can see that they're not perfectly parallelized because one of them is waiting for a lock, the other is holding. Another example, and this is a real example from MySQL. This is a database, it's an old example from 2008 or so based on a paper that we wrote. But basically, there's a critical section that all threads need to go through, and there's a parallel section. And this is what the result scalability curve looks like for this application. This is the number of cores that you add, and this is the speed up that you get compared to a single thread version. You can see that it increases, it peaks at 6, and then starts dropping down. So basically, you get a lot of synchronization overhead after 6 cores. Why? Because you're communicating all of these locks. Each thread needs to lock so that they can get to the parallel section, but they're really contending for the critical section over here. So there's overhead, and we will see that. And we'll see that you can actually solve this problem in some way, but I'm not going to talk about that right now. So barriers, we've also seen this, as you can see. These are parallel parts, but because one thread reaches the barrier much later than the other thread, it's not perfectly parallelized. And then stage of pipeline programs, that's also we've seen. If you look at it, this is a parallel part of the program. In fact, pipeline parallelization can make everything completely parallel potentially, but you can see that each parallel part is not perfectly parallel because one thread takes much longer to execute. Okay, so let me discuss this and then we'll take a break. But basically, these also lead to difficulties in parallel programming. You have little difficulties, parallelism is natural, like embarrassingly parallel applications. A lot of GPU type applications actually have been successful because we have relatively little difficulty, relatively I say, right? In these multimedia, physical simulation, graphics, for example, you have millions of pixels. You're doing the same operation on all of those pixels. That sounds great, right? That's perfectly parallel, basically. Once you start introducing the interdependencies, like once you start doing ray tracing, for example, going through all of those pixels in an irregular fashion, that becomes more difficult, right? So large web service databases, difficulty is usually in getting parallel programs to work correctly, and especially when things are irregular, and also optimizing performance in the presence of bottlenecks. So much of parallel computer architecture is really about both of those. Designing machines that overcome the sequential and parallel bottlenecks to achieve higher performance and efficiency. And also, hopefully making the programmer's job easier in writing correct and high performance parallel programs. So don't forget this correct and high performance and efficiency. Those are important. Because if you don't care about any of those, designing parallel machines is easy, right? But usually it's hard because you need to design machines that overcome these bottlenecks, because those bottlenecks actually kill you compared to a single processor, right? And we've already seen you should not make any mistake in terms of algorithms also. Your algorithm should be best for a single processor. Okay, so we're going to talk about both of these. Before we get into it, I think you've seen the parallel application memory scheduling paper, but we're going to talk about in a later lecture how to accelerate these bottlenecks, like critical sections, more general bottlenecks, and how to take into account utility. And you're going to get exposed to that. And you can find them if you're interested. You can look at them earlier. This is last year's incarnation of this lecture, of this class. Okay, I think this is a good time to take a break. What do you think? Okay, let's take a break. Let's come back at 3:15, and then we will hopefully finish memory ordering. We'll see. That's 15:00. That's basically 17 minutes. I guess that could have been misinterpreted as 15 minutes also. But it's really 17 minutes. Okay, let's get started. So now we're going to dive into one of those issues that is important for correctness. And I've already covered these slides. Basically, we're going to look at making the programmer's job easier in writing correct parallel programs, not even high performance. We're going to talk about performance issues a little bit toward the end. But I will start with saying that we've kind of seen this trade-off in a different way. And performance versus correctness. These are actually two metrics that are fundamentally at odds with each other. If you want to get high performance, you can guess the result of a program, right? This program that's going to do this matrix vector multiplication is going to produce 5. That's my high performance program. I computed in 1 second. But it may not be correct, right? You can, of course, do a more educated guess. So this is an example demonstration of performance versus correctness. You can just randomly guess a value. But this is actually true in many, many design choices also. You can always improve performance at the expense of correctness. Sometimes unintentionally, you forget some critical lock in your program. You get very high performance, but your program sometimes produces wrong values, right? It happens. You can design your architecture to ignore some ordering of operations. Again, maybe it doesn't happen often, but sometimes it becomes bad, right? And we will see examples of this in fundamental support for multiprocessor operation, MIMD machines, basically. And we're going to talk about memory ordering, consistency, and later we're going to talk about cache coherence. And these are examples where you can improve performance intentionally or unintentionally by ignoring some correctness issues. If you ignore them carefully, maybe you don't run into them much, but that doesn't mean that your machine is necessarily going to function under all conditions. So this is, I consider as a not real trade-off between performance and correctness, right? Because you're basically making your machine incorrect or under some conditions, either intentionally or unintentionally, and then you're gaining performance out of that. That's probably not good in general. But sometimes there's a real trade-off between performance and correctness. And this we have seen already, when the application or user can tolerate the resulting errors, right? So this can be done in a methodical way. If you can do it very carefully and methodically, you can actually gain benefits, right? We've discussed this, for example, in the past when we talked about reducing latency, reducing voltage, designing different types of memories that have different reliabilities, and partitioning your application based on its error tolerance across different pieces of memories, right? So I'm not going to go into that again, but if you remember, this was one of the papers that we discussed, exploiting the performance correctness trade-off, and this was another paper that is even earlier that exploits that. And we've had lectures on this, so I will not talk about that in more detail. So that's real, basically. There you really understand what you're getting by making your machine less correct or less reliable, and as a result, you're gaining performance, efficiency, or on some other metrics. If you can tolerate that, that's good. But performance versus correctness is very similar to the latency reliability trade-off. Reliability is at the hardware component level, like we've seen in memory. Correctness is at the program semantic level or at the hardware function level. So you can think of it this way, basically. And we've seen examples of the latency reliability trade-off before. I've shown that. And we've actually made use of it for good purposes, right? We reduced the latency, we got errors, and we actually took advantage of them to create device signatures, for example, or get random numbers and do other stuff like clock operation, which Altabak talked about a couple of weeks ago, right? So basically, it's a real trade-off, and you can read more about it. So memory ordering is actually very related to it, except this is not a trade-off, I would say. You really want to make something work correctly, otherwise a programmer will go crazy, as we will see. So these are some required readings. Well, this is the first one, is a 2-page paper that introduces sequential consistency, which is a very strict form of memory consistency, as we will see, but it's a correct form of memory consistency. And also the first one to recognize the problem. But later, there are some of these very interesting papers that talk about things. I'm going to mention them also when we get to it. But first, let's distinguish memory consistency from cache coherence, because these things are related to each other, but they're very different. And in real systems, you need to take into account both. But we're going to distinguish them and focus on memory consistency in this lecture. So consistency, as it will become apparent, is really ordering of all memory operations from different processors. You have different processors, They send memory operations to memory, and you're basically trying to order those different operations that go to memory. So you basically impose an order to different memory locations. Basically, you have a global ordering of accesses to all memory locations. And this is about consistency. We will see why this is important very soon. Cache coherence is about ordering of operations from different processors to the same memory location. Basically, we are concerned about the single memory location, not all of the operations that the processors are doing, a single memory location. And we're concerned about what happens to it. It's essentially a local ordering of access to each cache block. Why is this important? Because one processor may cache that location in its cache, another processor may also cache it, and one processor writes to that location, the other processor has stale value. So cache coherence is very different. It's about a single location, whereas consistency is about all locations that you touch. So both of them actually cause difficulties in multiprocessing. Basically, they cause difficulties in getting high performance and efficiency, and they cause difficulties in programming, parallel programming, in a correct and high performance way. So let's start with the fundamental ordering of operations. So you have, let's say, 4 operations, A, B, C, D. These are memory operations, but you could also apply to computation, but memory is much more interesting because memory implies communication and tightly coupled multiprocessors, right? The question is, in what order should the hardware execute and report the results of these operations? That's the question we're dealing with, basically. So this is really a contract between the programmer and the microarchitect. It's really specified by the ISA, instruction set architecture. Basically, preserving an expected, or more accurately, agreed upon order that's written in that contract simplifies programmer's life, because now the programmer knows what to expect. They basically write a program with A, B, C, D, and they get results in that order. That's called the sequential order. Okay, so basically, why does it simplify programmer's life? Because programmer doesn't go crazy. They can easily debug the applications. They can recover the state. They can do exception handling, all of those stuff without going crazy. So we talk about this when we talked about precise exceptions, precise state semantics in digital design and computer architecture, for example. But that's one example of ordering. But preserving an expected order usually makes the hardware designer's life difficult. And why? Because the programmer, the hardware needs to reorder the operations in some way. They cannot the hardware cannot freely execute things without thinking about an order. Right? And clearly, designing hardware is a lot easier if you freely execute things without thinking about ordering at all. Especially if the goal is to design a high-performance processor. And we've discussed load store queues in out-of-order execution and their complexity in digital design and computer architecture. I'm not going to talk about that, but you can watch some lectures related to that. That's perhaps the most complicated part of an out-of-order processor today, basically, to satisfy the load store ordering that's dictated by the program. But it's there for a good reason. The programmer has a sequential order of operations, and the hardware satisfies that sequential order. Okay, so let's talk about memory ordering in a single processor, which is a simpler problem, but it leads to a lot of complexity in existing processors. It's specified by the von Neumann model today. And von Neumann model, if you remember, it has 2 key properties, 2 fundamental properties: sequential execution and stored program. Sequential execution is what we're concerned about here. Basically, you have a sequential order, and hardware executes the load and store operations in the order specified by the sequential program. Makes sense, right? Out-of-order execution executes operations in some other order, but it doesn't change the semantics. Meaning hardware retires or reports to the software the results of the load and store operations in the order specified by the sequential program. Internally, it does something else, but externally, when it's communicating to the software, it finishes instructions in the order that is specified by the program. So it doesn't change the semantics. It does change the underlying latencies, though. So the advantages of sequential ordering in a single processor is architectural state is precise within an execution, and architectural state is consistent across different rounds of the program. So as a result, you have easier to debug programs. You can add, if you have a bug in your program, you know exactly what is executed and what is not executed, right? What has committed the results, what has not committed the results. The instruction that has caused the exception should not have committed the results, and no instruction following it should have committed the results. And all of the other instructions should have finished so that you can debug things nicely. Of course, the disadvantage is preserving this order, the sequential order in hardware, while getting high performance using out-of-order execution adds a lot of overhead. It can reduce performance of out-of-order execution. It increases complexity, it reduces scalability. This is the difficulty of building a large instruction window, basically. Large instruction window, you cannot finish you cannot retire an instruction if it's not complete. And if that instruction takes 5,000 cycles, well, how do you actually tolerate that latency? You need to build a large instruction window, and you need to keep ordering across all of those operations, especially loads and stores. So this is basically the story in a single processor, and we've discussed a lot of this in digital design and computer architecture. So you can look at that. We're going to make things more complicated. Make sense? Okay. So basically, as I said, this is an example. Ordering is good for the programmer. Programmer can reason about things. They can debug. They don't go crazy. Bad for the hardware designer. The hardware designer now needs to deal with that ordering and preserve that the semantics of ordering is preserved. Ensure that the semantics is preserved. Now let's take a look at an extreme case, which is a data flow processor. Now, if you recall, a data flow processor is a processor where ordering is specified only by data dependencies. There's no single flow of control. It's very different from the von Neumann model. An instruction executes when its operands are ready. And it's basically a data flow dependence that enables the execution of instructions. No program counter, basically. So a memory operation executes when its operands are ready. So in other words, two operations can be executed and finished, completed, reported to software in any order if they have no dependency. Now, the advantage is huge amounts of parallelism, and you can again watch the data flow lectures. You get high performance. Disadvantage is no precise state, no ordering semantics, basically. In pure data flow, you don't have any semantics. Ordering is not dictated. As a result, it's a huge beast to program. Basically, you cannot maintain precise state. There's no specified order. As a result, you get a very hard to debug machine. And that's why pure data flow has not been successful in real life. And also, there's another issue. Order can change across the runs of the same program. This is very hard to debug. We'll see that we're not going to be able to tackle that easily. This is actually very tough to tackle in a multiprocessor machine. This is why some of the multi-thread bugs that appear based on some ordering, but that don't appear based on some other ordering, may not be able to get detected easily. They don't appear all the time, basically. They appear in some executions. Okay, make sense? This is data flow story, which is exactly opposite. So MIMD, or multiprocessor, is somewhere in between, basically. Each processor's memory operations are in sequential order because each thread is sequential, obeying the von Neumann model. With respect to the thread running on that processor, basically, we're assuming that each processor obeys the von Neumann model, as I said. But multiple processors execute memory operations concurrently right now. Now, does this cause any problem? Basically, how does the memory see the order of operations from all processors? You may say, okay, is this an interesting question to ask? In other words, what is the ordering of operations across different processors? So why does this even matter? Let's talk about that basically. So there are three major reasons why ordering of operations across different processors matters, even if each thread obeys the von Neumann model, sequential execution basically. The first reason is ease of debugging, which we're not going to solve. Essentially, it's useful to have the same execution done at different times, to have exactly the same order of execution, because this provides you repeatability. You have the same program, same input. It's a parallel program. You execute it once, you get the same order of memory operations. You execute again, you get the same order of memory operations. You execute again, you basically get the same order. Now, this is nice to have, but it's very difficult to satisfy this because different threads can be scheduled at different times. They can get to the different lock at different times. So ordering actually usually changes across different programs. I'm not going to talk about that, although there's research to this end. For example, a lot of record and replay research, especially for debugging parallel programs. What you can do is you can record the execution while you're debugging. And then when you actually want to repeat the execution, you replay the same order. You can actually do this in virtual machines, etc. Yeah, but it's a lot of overhead basically to do this record and replay. But that's not the only way of doing it. That's a major way of doing it. But we're not going to basically talk about that. We're going to talk about correctness. Basically, can we have incorrect execution if the order of memory operation is different from the point of view of different processors? Well, the answer is going to be yes. That's why we're going to talk about it. But it may not be intuitive why the answer is yes, as we will see. So I'm going to give you an example, intuitive example. And then there's the performance and overhead. Basically, if you enforce some strict sequential ordering, this can make life harder for the hardware designer in implementing performance enhancement techniques like out-of-order execution caches, and we will talk about that also. So basically, we're going to start with correctness. We're not going to talk about the ease of debugging because that's not what we're going to solve. And then we're going to try to make it a little bit higher performance, hopefully today. Any questions? Okay, now let's start. When could order affect correctness? Because this is really what's fundamental. And it's really when you're protecting shared data. Because if the threads are completely independent of each other, they're not communicating at all, this order really should not matter, right? You think about completely parallelized program. Each thread is operating on a different part of the image. And what one thread is doing is not going to affect the other one at all. You're basically operating on the individual pixels. Each thread has one pixel, let's say, and you just basically change the color of that pixel. That's the goal. Then the ordering should not affect anything. Everything can be parallelized, right? That makes sense, hopefully, because you're completely independent between threads. The problem happens when threads are dependent on each other, meaning they're operating on some shared data. They're communicating with each other. And basically, when you're protecting shared data. So we're going to go back to protecting shared data, which is critical sections, right? Well, that's one way of protecting shared data, clearly. Threads are not allowed to update shared data concurrently for correctness purposes. Access to shared data are encapsulated inside critical sections or protected via synchronization constructs that lead to a critical section, like locks, semaphores, condition variables, whatever your favorite synchronization constructs may be. But the key invariant is that only one thread can execute the critical section, a given critical section at a given time. This is the mutual exclusion principle that has been developed on parallel programming. And if you've taken a parallel programming course, you might have seen it. Basically, the invariant that we want in the hardware is that a multiprocessor should provide the correct execution of synchronization primitives to enable the programmer to protect shared data. Right? Because if you're not protecting shared data, it doesn't matter. Right? That's basically, hopefully, that's understood and given. Whenever you're communicating, you have a problem. And if the hardware doesn't allow you to correctly execute a perfectly correctly synchronized program, then you have a problem. Right? Basically, the multiprocessor hardware should give you that correct execution semantics for the synchronization primitives. Now let's take a look at how mutual exclusion is supported. So I'm going to assume that programmer correctly ensures mutual exclusion. That's not, as I said, that's not the subject of this course. There are a lot of issues over there, of course, at the software level that people need to deal with. And there's also another correctness performance trade-off over there. If you don't do a good job synchronizing your programs, you may actually run into correctness issues at the higher levels. But basically, programmer needs to make sure synchronization is correctly implemented, threads are properly synchronized. And clearly, this is an important topic that's out of the bounds of this course. And a seminal reading on this is Dijkstra's Cooperating Sequential Process. How many people have read this? Was this assigned in any parallel programming course? This is so fundamental. You guys should read this. If you're doing any type of parallel programming, you cannot avoid Dijkstra. Dijkstra talks about this in 1960s, and this is basically his manuscript related to that. I mean, before Dijkstra, Dekker talked about it. There's Dekker's algorithm for mutual exclusion, which a version of it I'm going to show, but I'm not going to show every bells and whistles of Dekker's algorithm. But basically, there are correct ways of communicating between processes, which Dijkstra was concerned about, which is synchronization essentially. But all of those ways require some hardware support, as we will see. Programmers should rely on hardware primitives to support correct synchronization. And if hardware primitives are not correct or unpredictable, programmer's life is tough. If hardware primitives are correct but not easy to reason about, the programmer's life is still tough, basically. Basically, we want to be correct first and also easy to reason about next. So let's take a look at an example of Dekker's algorithm, kind of butchered, so that we can actually look at it, look at the execution in a nice way, let's say. So we have two processors, P1, P2, and there's a critical section in the middle, as you can see over here. Both of them are going to execute the critical section. Let's take a look at the perspective of one thread executing on processor 1. Basically, the way we're protecting the critical section is F1 equals means that 1 means that I'm going to take the lock in this critical section. This is one way of synchronizing. The else needs to behave correctly for this to work, of course. So basically, thread 1 over here sets F1 to 1, saying that I'm going to enter the critical section, and then checks if F2 is equal to 0, meaning processor 2 is not in the critical section. If F2 is equal to 0, processor 2 is not in the critical section, and then processor 1 goes into critical section. At the end of the critical section, sets F1 to 0, indicating that it's not in the critical section anymore. And then it does whatever it needs to do afterwards. Right? Processor 2 exactly does the same thing. It sets F2 to 1, and then checks if F1 is 0. If F1 is 0, that means processor 1 is not in the critical section. Then it can enter the critical section, execute it, set F2 to 0, and then move on. So basically, if this check fails, you jump into else, and then you basically retry. So there needs to be something in the else to make sure that this works correctly, and that's what Decker's algorithm does. That's the software level. I'm going to ignore that. We want to make sure this works correctly. So if you think about it, this kind of makes sense, right? Yes. Yeah, absolutely. Those are synchronization variables right now. Yes, exactly. But that's what we're going to talk about in the memory consistency model. There needs to be some operations to ensure that that sort of thing doesn't happen, basically. So there are multiple ways of doing it. You can somehow support some atomicity in the processor. Yeah. This could be one way of doing it. But I think you have a good point, basically. There could be another way of designing this program. Okay. So basically, only P1 or P2 should be in the critical section at any time, but not both, right? That's what we want to guarantee over here. So assume that P1 is in critical section. Intuitively, it must have executed A, right? A is this one now, F1 equals 1. Which means F1 must be 1, as A happens before B. Which means P2 should not enter the critical section, right? Does that make sense? Maybe you can leave your question for later. Let's discuss this first. So now we're talking about basic happen before relationship. If F1 is, if P1 is in critical section, it must have executed F1 equals 1, which means F1 must be 1, and which means P2 should not enter the critical section, right? Okay. So timing becomes an issue, as we will see. So the question is basically, can the two processors be in the critical section at the same time, given that they both obey the von Neumann model? That's the only thing they obey, basically. And the answer is going to be yes, basically. So we're going to assume something like this. We're going to play with latencies, basically. Let's take a look at it. I should ideally cover this, but anyway, we don't have a whole lot of time to draw this. But basically, ignore what's at the bottom. Let's take a look at time 0. Processor 1 sets F1 to 1. That's A. And F1 is equal to 1. It's complete from processor 1's point of view, basically. Processor 2 sets F2 equals to 1. And F2 equals 1 is complete processor 2 from processor 2's point of view. And then processor 1 sends A to memory, which is setting F1 to 1. And then processor 2 sends X to memory, which is setting F2 to 1. Now, these are going to take long, basically. F1 is over here, and F2 is over here. Each processor will take long to access the respective things that they're going to set. Right? But from the processor's point of view, these are done. I wrote to memory, and I'm done. I don't care about what memory does. Right? That's the von Neumann model. Doesn't care about what memory does and how the execution appears to other processors. Now, processor 1 goes on to B. It tests F2 is equal if F2 is equal to 0. F2 is somewhere else, which is here. Basically, it sends a request to the memory system, and this load of F2 gets started. It's going to complete earlier than writing to F1. And then P2 does the same thing, except it's testing F1, whether processor 1 is in the critical section, basically. So it loads F1 from memory, and that load gets started, gets sent to the memory system over here. It's going to take some time. Let's assume that 49 cycles later, memory sends F2 to processor 1, because this is in a different bank, and it goes to processor 1. And memory sends F1 to processor 2, as they requested in the load, basically. And then you can see that initially F2 and F1 are 0. So memory sends both of them 0 values. So now load of F2 is complete over here, and it's this B operation is complete. So the processor 1 thinks F2 is equal to 0, and processor 2 also thinks F1 is equal to 0, because they were both 0, right? Because these operations completed before the writes to memory completed. Now both processors entered the critical section because both of them thought that the variables that control entry into the critical section are both 0. Right? Okay. Now this is not good. Clearly, this is not what we wanted, right? Now memory completes A at some point, which is setting F1 to 1. And this is too late, clearly, because something else happened in memory that sent the old value to processor 1. And then memory completes X, to processor 2, sorry. And then memory completes X, and F2 is set to 1 in memory. But this is too late. Okay, so you can go through this yourself, but basically the key takeaway is processor 1 wrote to a location, assumed that that was done and visible by some other processor. Processor 2 did the same thing, wrote to a location, assumed that that was done, and it proceeded, basically. So what happened? Let's examine each processor's view. This is the same thing that I showed you earlier. Now, if you think about it, if you pull back a little bit, look at the ordering of operations. Processor 1's ordering was A executed before B, which is fine. And then critical section executed after that, which is fine, basically. So processor 1 did not violate anything. From processor 1's perspective, this is one Neumann model, no problem. From processor 2's perspective, again, X executed before Y, as it should, and then critical section executed after that, and then you go into whatever we did not cover. But basically, from the processor 2's point of view, again, no problem, one Neumann model was obeyed, right? But what was broken over here is the from memory's perspective, you have conflicting views, right? So processor 1 and processor 2 both saw an inconsistent order of operations in memory. So processor 1's view, let's say, A happened before B, which happened before X. Processor 1 saw X later, right? It's too late, basically. So from processor 1's perspective, A happened before X. From processor 2's perspective, X happened before Y, which happened before A. So from processor 2's perspective, X happened before A, essentially. Now, clearly, one of those can be correct. Right? Both cannot be correct. And this is the problem you have, basically. You have a happen before relationship violation if you don't impose some other ordering. Both of the processors are executing the von Neumann model, and both of them are seeing a different order from their perspective. Make sense? So this is essentially the problem. So for P1, A appeared to happen before X. For P2, X appeared to happen before A. And that's essentially, I said, that the processor did not see the same order of operations to memory. And this is a very fundamental relationship, clearly, right? If you're programming, you need to really, if you break this happen before intuition between different threads that you're writing, then you have a problem, probably. Right? This is actually very important in distributed systems also. Essentially, the happen before relationship between multiple updates to memory was inconsistent between the two processors' point of view. As a result, each processor thought the other was not in the critical section. And as a result, you get an incorrect result problem. Right? Okay, so how can you solve the problem? Basically, of course, you can change the program, but changing the program doesn't really change the fundamental issue with this, which is really the happen before relationship being broken. And that's what people try to restore, right? Yeah, and the idea is really sequential consistency in this case. Well, that's one idea. But basically, that's Lamport's idea in 1979, and you can read the paper that he discussed. And he basically says all processors must see the same order of operations to memory. In other words, all memory operations happen in an order called the global total order that is consistent across all processors. That's the idea. Now, there could be many different global total orders. They could appear in different executions, but you want, in a given execution, all processors see the same global total order. Now, the assumption is that within this global order, each processor's operations appear in sequential order with respect to its own operations. This means that each processor still preserves the von Neumann model. Because if you break that, then there are other issues that come about. We're still assuming von Neumann model over here. And that's essentially what this two-page paper talks about. I think we already said both of these. I'm not going to talk about. You need one Neumann model, plus the result of any execution is the same as if the operations of all the processors were executed in some sequential order. That's another way of saying that you have actually a global total order of memory. Okay, so this is a memory ordering model now. It's not an instruction ordering model like the von Neumann model. It's really a memory ordering model or memory model. This has to be specified by the ISA. And if it doesn't get specified by the ISA, you may run into issues like we have shown earlier. And it's really a programmer's abstraction also. If you think about sequential consistency, you can think about a picture that looks like this. Essentially, memory is a switch that services one load or store at a time from any processor. And all processors observe what's going on, and they see the currently serviced load or store at the same time. Each processor's operations are serviced in program order. That's von Neumann. That's the idea. Does that sound good? Now, it sounds, this will actually fix the problem. This does fix the problem. But you get a bunch of potentially correct global orders. In the previous example, all of these are correct global orders. So if you go back to this picture over here. So you want to make sure that all of the processors see A, B, X, Y in some order, right? They could be in any order, actually. And if you look at these, A, B, X, Y, A, X, B, Y, A, X, Y, B, X, A, B, Y, X, A, Y, B, X, Y, A, B, all of them are correct. Each individual processor obeys the von Neumann model, of course. Which order, each of these are also called an interleaving, is really observed based, which order is observed depends on the implementation and the dynamic latencies. Basically, how long does it take to execute the operation? Which bank is the update happening to? Which what is the interconnect latencies, basically? So ordering is very much dependent on where the data is and how long it takes to access the data, basically. That's why when you run a parallel program multiple times, you get different orderings. And you get different because the latencies change. The caching is different. The dynamic behavior is different. As a result, you can get different orderings. And this is one of the reasons you may actually get difficulties in debugging your programs because you cannot replicate exactly what's going on. What record and replay mechanisms do is they basically fix the ordering in one way, and then you always get A, B, X, Y, for example. Of course, that may not be great for performance, right, under some conditions. Okay, so a corollary is basically, within the same execution, all processors see the same global order of operations to memory. There is no correctness issue now. We actually got rid of that without changing the programs that we have. But as you change the programs, you will see that you will actually need something like this at a higher level later on. Basically, whenever you're synchronizing, you need to actually provide this. There's no correctness issue. This satisfies it happened before intuition. And across different executions, different global orders can be observed, each of which is sequentially consistent. Basically, debugging is still difficult because order changes across runs. But at least we got rid of the correctness problem. Okay, and this is a paper from 1979. This is going to be a reading that you do. Easy reading, I think. It's dense. Now, the issue is sequential consistency works, and a lot of processors early on were sequentially consistent. But unfortunately, it has two conservative ordering requirements. And it also limits the aggressiveness of performance enhancement techniques because of this. So basically, the question is the total global order requirement too strong? And people have actually asked this question a lot. Do we need a global order across all operations and all processors? Global total order, is that what you want? And then people question this basically. How about a global order across only stores? Because that may make things, that is where things really get updated. So total store order is a memory model that's employed in x86, for example. Unique store order, that's another name for it. How about enforcing a global order only at the boundaries of synchronization? Because that's where you actually are communicating between different threads, right? And people actually design weaker memory models for this. These are called relaxed memory models or weaker memory models and acquire release consistency model, as we will see. Okay, any questions so far? Yes. Yeah. That's a great question. I guess, is it possible to really check? Yeah, it requires a lot of hardware, I think, right? Yeah. I think people have actually proposed mechanisms like this in a lot of research papers, but a lot of them basically boil down to requiring a lot of, essentially keeping a record of the ordering and then comparing it to other orderings that are seen. They do it. You can do it using Bloom filters and things like that, but it's actually, people have shown that it's very costly. That's a good idea, I think, though. Maybe if they can do it, if you can do it with low overhead, potentially you can do that.
I think there is also papers that perform like speculative execution on that, like they just speculate on that. But I think, remember for one of your lectures, they gave up on that because like to replace the perfect like to undo all the operation is very costly, so that they don't employ this.
Yeah, I mean, you can do speculative execution, but you still require synchronization, proper synchronization primitives, because you need to know what went wrong, right? So in speculative execution, you also need to record what went on in different parts. Yes. Okay. Any other thoughts? This may be not so easy to understand, so I would recommend going through the example on your own if you haven't fully understood it. Once you understand, it's going to be easy. But yeah, consistency issues have plagued, let's say, compilers as well as architecture for some time. Okay, so let's talk about the global order requirement being too strong. So essentially, performance enhancement techniques that could make XC implementation difficult exist already, actually, while people were thinking about SC, even then people were talking about out-of-order execution. For example, loads happen out of order with respect to each other and with respect to independent stores. And this makes it difficult for all processors to see the same global order of all memory operations. Caching was developed in the 1960s, right? A memory location is now present in multiple places. And if you actually have a cache, this prevents the effect of a store to be seen by other processors, right? Now, this makes it also difficult for all processors to see the same global order of memory operations. Now, caching makes it interesting because it also leads to cache coherence issues, which is about a single location, but also leads to ordering across multiple locations, not be visible to other processors. So people have developed weaker memory consistency models because of these reasons, essentially. Essentially, the ordering of operations is important when the realization is that the ordering is important when the order affects synchronization on shared data, right? Operations on shared data. In other words, when processors need to synchronize to execute a program region, right? So weak consistency says somebody, programmer usually, specifies regions in which memory operations do not need to be ordered with respect to different processors. And this is already done in existing processors. Memory fence instructions delineate those regions. This exists in almost all ISAs that I know of. And the way it works is all memory operations before a fence must complete before the fence is executed. And all memory operations after the fence must wait for the fence to complete. Basically, it's a barrier, or it's also called memory barrier, actually, in some ISAs. It's called memory fence in some other ISAs. It basically says everything before this barrier should be finished before the fence is finished, and everything after the barrier, every memory operation, should wait for the fence to finish. So it separates the memory operations before the fence and after the fence such that there's no overlap between those operations. And this helps. I mean, you can immediately imagine that you have a fence before you actually access some synchronization point, right? So fence is complete in program order, essentially. And all synchronization operations act like a fence, essentially. And if you think about it, if you reason about it, and there are papers written on it, this actually works, and it's actually better than sequential consistency in terms of the ordering requirements. The difficulty now is it's more burden on the programmer, right? Previously, the programmer didn't need to do anything. The programmer just wrote a program, hopefully correctly synchronized, and it worked sequentially consistently. Now the programmer needs to think about, okay, where do I put my fences? What are my fences, right? So they need to be more careful about synchronization, basically. And they may actually run into correctness issues at that point, right? So there are actually good papers on this. This is a paper that I recommend. It was written, as you can see, almost 31 years ago. Basically, maybe the strictest model, as you can see, is proposed by Lamport. And basically, people have developed different models to impose ordering. Basically, should there be ordering between loads and stores, loads and stores, loads and loads, loads and stores, stores and loads and stores and stores. Basically, some models basically get rid of the store load ordering, assuming they're not dependent on each other, for example. This doesn't need to be visible. We can, essentially, this arrow says V, the end of the arrow, the operation at the end of the arrow cannot be performed until the operation at the beginning of the arrow is performed. Sequential consistency basically requires ordering across all operations. But you can eliminate some of the orderings over here, as shown in this paper, right? I guess I don't want to read this necessarily, but maybe I'll read one sentence over here. Processor consistency relaxes some of the restrictions imposed by sequential consistency. Processor consistency requires that writes issued from a processor may not be observed in any order other than that in which they were issued. Okay, so however, the order in which writes from two processors occur as observed by themselves or a third processor need not be identical. You need to basically think about it to parse it. But basically, it relaxes the order. And then you need to formally prove this, of course, to make it correct. Okay, and then let's talk about even weaker memory models. You can see that, I think I'll read it from here because it's actually a nice written paper. A more relaxed consistency model can be derived by relating memory request ordering to synchronization points in the program, essentially requiring ordering at the synchronization points. For example, the weak consistency model proposed by, based on the above idea and guarantees a consistent view of memory only at synchronization points. As an example, consider a process updating a shared data structure within a critical section. Under sequential consistency, every access within the critical section is delayed until the previous access completes. But such delays are unnecessary if the programmer has already made sure that no other process can rely on the data structure to be consistent until the critical section is exited. We consistently exploit this by allowing accesses within the critical section to be pipelined. So basically, correctness is achieved by guaranteeing that all previous accesses are performed before entering or exiting each critical section. So this is weak consistency over here. You have acquire lock and then release the lock, and then there's a critical section. And then there's something that happens after the critical section. And then there's another critical section, acquire another lock and release another lock, and there's a critical section. Basically, the only things that you need are these arrows in weak consistency. You can see that nothing over here should execute before this happens, and nothing. Basically, the ordering requirements. The ordering requirements is such that the ordering of acquires and then this block and then this release and then this block and then this acquire and then this block and then this release should be consistent across all processors, basically. So we basically don't delay operations that happen inside the critical section or outside the critical section within each other. And then you can actually make it even more weaker. And that's what's proposed by this paper, which is release consistency. Okay, let me go back over here. Essentially, people have realized that as long as the acquires are ordered with respect to acquires and releases are ordered with respect to releases, and you have a consistent order across different processors, you can execute all of the other operations in some other order for a properly synchronized program. Again, so that's, again, this may not be very easy to understand. And in general, these topics are not easy to understand. You need to think about them. It requires some time to think about them, frankly. But let me actually read this over here. Release consistency is an extension of weak consistency that exploits further information about synchronization by classifying them into acquire and release accesses. An acquire synchronization access, a lock operation or process spinning for a flag to be set, is performed to gain access to a set of shared locations. A release synchronization access, for example, an unlock operation or a process setting a flag grants this permission. An acquire is accomplished by reading a shared location until an appropriate value is read. Thus, an acquire is always associated with a read synchronization access. Similarly, a release is always associated with a write synchronization access. So basically, now we're distinguishing just the synchronization accesses. In contrast to WC, unfortunate naming, I guess, weak consistency. Release consistency does not require accesses following a release to be delayed for the release to be complete. The purpose of the release is to signal that previous accesses are complete, and it does not have anything to say about the ordering of the access following it. So this is really critical, basically. Sequential consistency is too strong because it's basically imposing an order. But these folks are saying that this release says nothing about the accesses that come after the release. The purpose of the release is to signal someone else can do something to this stuff over here. So if you have a properly synchronized program, why are you delaying the stuff that comes after the release? So that's the realization. And you may say that this may be intuitive, but it takes some time for people to realize. You start with a very strong assumption, and you basically weaken the assumptions over time. So I think this paper is actually quite insightful if you start deciphering what it says. Similarly, release consistency does not require an acquire to be delayed for its previous accesses. Basically, this is the other realization. The other realization is that, this acquire over here for this critical section has nothing to do with the prior accesses over here. So this acquire does not need to be ordered with respect to these accesses over here. That's the idea. And then it boils down to basically, you really need to have ordering across the critical sections, essentially. Okay, if you didn't understand that fully, I would recommend reading this paper. It will be part of your reading list, even though it's an old paper. And there's a lot to be said over here. Any questions? Okay, let's talk about weaker consistency. Let's pull back a little bit. There's also a lot of implementation issues that I'm kind of ignoring over here, right? How do you implement these things? But basically, the advantage of weaker consistency model is there's no need to guarantee a very strict order of memory operations, essentially. That sounds good, right? This enables the hardware implementation of performance-enhanced techniques like out-of-order execution and cache coherence, caching to be simpler. It can also be higher performance than stricter ordering because you're not strictly requiring the ordering or like sequential consistency. Because if you think about it, implementing sequential consistency, maybe we should have thought about this a little bit, but implementing sequential consistency requires all of the processors seeing exactly the same order, which means that internally, what you did in the processor needs to be exposed outside, right? So you cannot basically do stuff like caching. You need to expose every access that you have to the memory or some synchronization point to everyone. This actually is not very good in terms of scalability of the system also. So basically, performance and scalability gets impacted significantly if you really require sequential consistency. You can overcome this by some other stuff, some other mechanisms, but in the end, you have to show what you're doing to every processor if you really are obeying sequential consistency strictly. So, but we could consistently get rid of that, essentially, that complexity as well as performance inefficiencies. Now, disadvantages, now you have more burden on the programmer or software. You need to get the fences and the labeling of synchronization operations correct. And if you miss them, if you've done parallel programming with fences, for example, in ISA, you will see that you have a problem. Now, the question is, of course, who does this? Well, if you're using libraries to synchronize across your threads, maybe you don't care about this. That's true. But somebody must write the libraries. And somebody must rely on correct hardware to write those libraries, right? You may be actually, if you're operating at a programming at a much higher level, you may be using libraries that are properly developed to do synchronization, and you may just be doing synchronization calls and you don't care about the ordering. But if you're writing libraries, then you really need to deal with this. If you're writing a compiler, you also need to deal with this basically because the compiler actually needs to know the memory model so that you can parallelize the application, for example. So this is another example of the programmer microarchitect trade-off. With a weaker consistency model, microarchitect's life is easier, but programmer's life is harder. This is another kind of a different kind of trade-off over here. And people over time basically said we should really make programmer's life a little bit harder, let's say. So sequential consistency makes programmer's life is really easy, but makes a lot of the operations very, very difficult to implement and hardware very complex. So people have actually moved to weaker models. But they didn't go all the way to this release consistency. So release consistency is really, let's say, extreme, I would say. I mean, there are some more extreme models also that automatically try to do this, for example. I'm ignoring that for now. But usually, what we have today is somewhere between sequential consistency and release consistency. There are weak models, like total store ordering is one example. A little bit weaker models also exist, but they're not all the way to release consistency because that requires a lot of burden on the programmer in the end. Yes, go ahead.
C++ tried more extreme memory ordering, like scaled relaxed.
Okay.
The only guarantee that you have there is like if you have two relaxed variables, they will never overlap each other.
Okay.
And you have consistency if they're existing on the thread. So okay. It's the only thing they guarantee you. So it make it really complex, but there is some application that actually benefits from that.
Yeah, sure, exactly, yeah. So I think you can choose that, right? Basically, you're not required to use that. Yeah. Is that correct? Okay, yeah.
They give you sequential, they give you a current release, they give you relaxed, and they give you another one that I forgot the name also.
Yeah, exactly. So, okay, here maybe I should also mention that there are two different kinds of consistency models. One is at the language level, and the other is at the hardware level. And these may not actually be nicely synchronized with each other also. So thanks for bringing it up, because at the language level, you also need to have this sort of model so that you can basically decide what kind of optimizations you can do in terms of compilers, right? Clearly, there are relaxed memory models that are enabled at the language level, like C++ or Java or whatever. And these models can enable the compiler to do much more aggressive optimizations, right? Because the programmer can say, okay, I don't care about this, and I can be very, very relaxed about these operations, and the compiler now has a lot more freedom to optimize. And then at the hardware level, we have another model, which is essentially a memory consistency model, which is another ordering model, but it's at a different level of abstraction. Here, the question is, what does the hardware guarantee in terms of ordering? So these two things also make things a little bit more complicated, but you need to think about, so relaxed models make compilers' life easier at the programming language level. Relaxed models make hardware designers' life easier at the hardware level. So essentially, the trade-off is the same, except who gets affected is different. Does that make sense?
It's like I was like following like the community when they're trying to work on this stuff, and I think many people was pointing out like it's not easy to see people from industry and people that works on compiler and hardware together in the same table to talk about this. Was the only way they could make it possible, because people was trying to work on different sides. It was not working. Only when they put all of them together in the same tables, well, they got like consistency.
Yeah. Okay, yeah, this is another area where people don't talk to each other necessarily, but they started a bit. Okay, so I think we've already covered this, yes. I went back. Okay, there's more on weaker consistency models. I think I will end almost here. Let's see if, oh, we still have time. Wow, you can still ask questions. But I will also mention that there's a lot of literature on this topic. In the end, I like pointing out this old paper because it actually answers a lot of the questions that later research also kind of converged to. But basically, this paper says that memory consistency model is important. Maybe we'll read it also. That's why I actually copied a lot of these over here. But basically, there are several attempts that have been made to relax the consistency models to allow for more buffering and pipelining of memory accesses. Unfortunately, the potential increase in performance afforded by relaxing the consistency model is accompanied by a more complex programming model. That's what we discussed, right? This paper introduces two general implementation techniques that provide higher performance for all the models. The first technique involves prefetching values for accesses that are delayed due to consistency model constraints. So prefetching actually can help overcome some of the problems because you prefetch the data and you use it, and then you expose the ordering later on. And this paper talks about how. The second technique employs speculative execution to allow the processor to proceed even though the consistency model requires the memory access to be delayed. When combined, the above techniques alleviate the limitations imposed by a consistency model on buffering and pipelining the memory accesses, thus significantly reducing the impact of memory consistency model on performance. So again, you need to read exactly how they do it, but what we have talked about, prefetching and also speculative execution, like out-of-order execution, alleviate some of the ordering requirements. You still need to satisfy, you still need to ensure that ordering is satisfied, but you can actually speed up the single thread by doing aggressive prefetching, aggressive speculative execution, and reporting the ordering, delaying the ordering for later on. And that's essentially how they do it. In a sense, it's kind of similar to out-of-order execution, right? In out-of-order execution, you execute a program in some order, and eventually you report the results. It's kind of like that. But here, when you're reporting the results, you need to the order that you have is not just this processor, it's really across different processors. So it's a bit more complicated than out-of-order execution. Okay, so this is what I will recommend. This is a different paper from the same author. Kurosh Garacharlu did a lot of actually seminal work on this topic. And you can see that I still reference those his papers. But there's other work in this area also that you can read. So this is actually a good topic for exam questions. This is an example exam question if you're interested. But basically, it's actually a good topic for programming and exam questions. It's not that hard questions in my opinion, but you can see an example. Maybe we'll go through this quickly. Yeah, talking about exam, I'll probably give you the date also. But essentially, you can see that two threads are concurrently running on a dual core processor that implements a sequentially consistent memory model. Assume that the value at address blah blah is initialized to 0. And then the question is, list all possible values that can be stored in R3 after both threads have finished executing. So this is a very simple value interleaving problem, basically. And there are multiple different possible values. If these are sequentially consistent, they're not hard to get. And the solutions are online somewhere. You can find them. And then another question is, after both threads have finished executing, you find that the register values are like this. How many different instruction interleavings of the two threads produce this result? You can also figure that out. You can see that there are only some possible instruction interleavings, at the end of which you get these values for R1, R2, R3, R4. Okay. And then what is the total number of all possible instruction interleavings? You need not expand factorials. Not that hard to get, but you need to think about it a little bit. And then on a non-sequentially consistent processor, is the total number of all possible instruction interleavings less than, equal to, or greater than your answer to question C? Good to think about. I'm not going to give you any answers, but these are actually good questions. And then there are other questions also which involve a little bit more thinking about the program also, but I'm not going to read all of this for you. You can find it online. essentially, this is a good source of questions. But this is also a good source of bugs, if you will. If you actually write code, and if you are writing very low-level code that does synchronization, you really need to know about what's going on. If you're writing with libraries that someone has optimized, you don't need to worry about any of this. Okay, any questions? Yeah, go ahead.
I would just realize that I talk about like the relaxed memory order in C++, but it's actually broken.
Okay.
So don't
Yeah.
use it. I think they missed some synchronization with hardware. I think they didn't take in consideration like hardware can predict values and somehow it affects the model of relaxed model. So don't use it.
I see. Okay. Yeah. There you go. So it's basically easy to get something broken in these, frankly. Especially if you're doing it at the programming language level, but also at the hardware level. Like if you actually do not correctly implement the consistency model, essentially your sum synchronization construct will be wrong. And you can always say, okay, who's implementing this? There's always someone in the world using that synchronization. At some point, some code will execute that basically. Basically, you cannot get it wrong. The performance versus correctness trade-off is not a trade-off, basically. This is very different from the performance versus reliability trade-off that we used earlier, right, for other purposes. Yeah, so there are a lot of stories like what you said in the past that have happened. And there are still bugs in the processors. Actually, if you go to the processor, microprocessor errata, people release errata of processors. A lot of them are related to multiprocessor operation. Consistency is one thing. Coherence is another thing. Basically, if you classify all of the bugs, a lot of the bugs are usually either multiprocessor operation, it's always there, or something that is released recently, that has been released recently. For example, when AMD released the virtual machine extension so that they can accelerate the virtual machines faster, in the next errata, those were a good chunk. Over time, they got reduced because those new extensions got implemented in a better way. People fixed the bugs. But the multiprocessor bugs are almost always there. They're reported. For legal reasons, people report it and say, okay, there's a bug like this. They don't exactly explain how the bug appears, but they're there. So it's not an easy part of the system to implement. Yes, you had a question. Yeah.
I have a very small question, but maybe very general. The thread in the software that we write, we usually spawn or fork a different process or different thread is not necessarily mapped to the thread we are talking about now and in hardware, right?
I mean, it is, yes, because when you spawn a thread in software, it's a hardware context. It's a context, and it's executed some hardware context. Yes, so the software thread gets executed in a hardware context.
You don't split the thread in software into little small threads anymore in hardware, or
no, that's not what we're saying. Basically, this the thread that you write in software is exactly what's executed in hardware as a thread in the hardware context. We don't split it later.
Okay, but then you are not utilizing later on, like, so this thread corresponding to one core in the CPU, not like multiple instruction per data.
That's right, yes. So basically, this thread is executing in one core, another thread is executing in another core.
Okay. Yeah.
Okay. Okay. If there are no other questions, then we're done for today. Because I'll see you tomorrow.